All right. Good morning, everyone. I'm Ray Zhu. I'm on behalf of our AISCC organizing team in here to thanks everyone to come. So, as the workshop name AISCC suggests, our workshop focus on the topic of AI system security, privacy, and safety, also along with confidential computing. Okay. So these two areas has gained a lot of interest from both the industrial and academic community. Oh, I'm sorry. Oh, oops. Sorry, we got some technical issue in here. Should I unplug it and re-plug it one more time? Oh, okay. Okay. So I'm not going to touch it anymore. All right. And also there's a tight interconnection between these topics. However, as what we found is there's no such workshop to bring them together. So inspired by this enthusiasm, about 6 months ago, the four of us organizers came together with the idea of hosting this workshop in NDSS. Yeah, before we start, I would like to appreciate, thanks for our sponsor. This workshop is supported by NIST and AirPass True AI project, and also the NSF CDCC project. All right, let's moving on. When we talk about how hard these topics are, I want to elaborate a little bit more. AI system has been super popular in the past couple of years. So I remember that in last year NDSS, someone mentioned that whenever you have a conversation goes to awkward silence, you can always bring up the magic word ChatGPT to the conversation to save the conversation. Indeed, yeah. We have witnessed the emergence of various impressive large. Yeah, we have witnessed the emergence of various impressive large language model, along with their significant concern regarding the security, safety, and privacy issue with these large model systems. On the other hand, confidential computing as a solution to data privacy issue has seen significantly advancement in hardware in recent years, particularly notable is NVIDIA's launch of H100, which has made confidential computing on GPUs. Many hospitals and banks are currently exploring the confidential computing to address this data privacy challenge. All right. So as a consequence, the use of a confidential computing solution for processing large models become increasingly common. The security and privacy issues that arise in this context are still relatively unexplored by both academia and industry. More importantly, there's a noticeable divide between the community in these two topics. Practitioners from both fields rarely intersect, leading to very limited opportunity for exchange and collaboration. So this challenge inspired the motivation behind organizing AISCC. For the first time through this workshop, we aim to provide a platform for AI and confidential computing community to interact more effectively. We hope that through this interaction, new research questions will emerge alongside innovative solutions and insights. All right, let's move on. Let me summarize the call for paper for this time. Firstly, regarding our technical program committee TPC members, we invited a total of 41 PC members with an even distribution of 21 PC from both AI and CC side. It's not because my mathematics is bad, but there's one PC expertise on both sides. So in here, 21 plus 21 is 41. Regarding submission, we received a total of 18 submissions, which is far exceed our expectation. These submissions were authored by individuals from 28 different affiliations across 7 different countries. So finally, there are 12 papers were accepted by presentation at the workshop. The accept rate is 66%. We also analyze a proportion of submission from industry and academic sectors. The blue bins in here represent the number of submissions, and the orange bins in here represent the number of accepted submissions. You can see that there are many submissions solely from academia. However, when it comes to the accepted rate, papers that represented collaboration between industry and academia got the highest accepted rate. Finally, regarding the topic distribution, we found that submission-related AI is significantly outnumbered those on the CC side. The acceptance rate for AI-related submission was also notably high. All right, so here's the plan. We're gonna first introduce our guest speaker in here, and after the guest speaker's keynotes, we're gonna give the distinguished paper award. After that, we will start our paper presentation. Yeah, so our first guest keynote speaker is Hubertus Franke, who is a distinguished research staff member from IBM. He's also an adjunct full professor of New York University. All right, yeah, I'm not gonna linger in here anymore, so thanks. It's your time.
You clap afterwards. Okay. Okay. There you go. So I talk about what we call the Accelerator Conundrum with confidential computing. So I'm Hubertus Franke, work for IBM largely, that's my main profession. I also want to give a shout out here to Meng Mei and Apur, who basically helped me pull all these data together so we collectively basically present here, okay? So when you effectively look, also one shootout here, you basically distinguish between AI people and CC people. I'm definitely a CC person, right? So to me, AI is a black box. I look at it as from a system perspective. What can I do, right? What does the workload do? How can I basically change things in the architecture or in the operating system where my expertise is, okay? So if we go back, right, over the last few years, AI workloads are literally changing everything, right? The way we basically consume data, how we basically making suggestions, but also how basically systems are being built, right? We see a significant rise in demand. Don't we all have wished to have bought NVIDIA stock about a year ago, right? We see significant rise in computational power that came with this demand, right? And when we look at this, many of these actually, from an application point of view, look more and more like HPC systems, right, of the past, right? With matrix, vector multiplication, and so on. On top of it, we see a significant energy expenditure, right? So you see on the right-hand side a picture from David Patterson, who kind of says, you know, just training one model is like riding 3 jetliners across the country, right? So if you look at the bottom left, models have become more and more complicated, right? So we all basically sitting at GPT-3. Now we see that effectively more and more models are being generated, even in private, like even, you know, IBM, for instance, has their own models for their reasons, okay? So if we basically look at the technology path, right, you can effectively say there are different generations. I mean, everybody has their own connotation and characterization of what these generations are, but if we go back in the 80s and 90s, there's probably computing was largely dictated by the area of PCs. Then we're basically going in the next generation, obviously, internet drove, particularly the cloud and the mobile space drove the invention. Many of, for instance, power savings inventions are coming now through mobile, right? And they're basically reflecting themselves back into the PC or into the regular computer architecture. And now one can state that the next generation most likely or is already being defined by AI and deep learning and other workloads, right? And you can see underneath, it's not just the area that's defined, so the usage defined it. There's a lot of innovation that's being done at the technological level. I do look back about 20 years, somebody told me 7 nanometers is absolutely the last thing that we can do. Now 2 nanometers, right? So never disbelieve or never, you always have to believe in that there is going to be an improvement, right? And if you believe in that, you will basically run on this curve. Now, since we're talking about confidential computing, just a few shots here at the security features, right? So if we hit a couple of numbers, I don't want to go through each and every one of them, right? But at the end of the day, you know, it's a substantial amount of money is being spent to basically make sure that the system does not go down. So for instance, you have to stop a threat before it disrupts a business, over $5 million, right? You have to deal with the data sprawl, right? So how do you make sure that data that needs to be kept confidential doesn't basically dissipate through other channels, right? On the right-hand side, you can actually also see that there are challenges, right? It, to some degree, is like more, it used to be that you would basically rely on processes to protect your data, right? You would basically bring things in the data center, you tie down the network, you tie down effectively who can log in and so on, so role-based. Now, that becomes increasingly a difficult process to go after. There's also, I would say, a lack of automation because of that, right? And effectively, cloud has helped us to automate things and standardize things, right? And then at the end, you also have different persona that ultimately come in. You have an engineer, right, who can say, I want to ensure that my applications are secure. You have a developer, right, who has to basically put certain things into their code in order to ensure that. And then finally, you have a compliance officer who ultimately has to ensure that these processes are being held. Overall, that's going to be processes that need to be put in place that make protecting data difficult. As a result, we continue to see that people try to keep data locked up in a data center. Okay? So let's look at the rise of confidential computing, right? Data is king, which I took off one of the links that I have at the bottom, right? Data has become pretty much the high value item that you need to, that you can extract value of. Take example, Netflix, take companies who effectively want to do targeted advertising, right? They look at data, they look at your interaction and so on, and out of that, through their specifics, derive value out of it, right? If you basically lose that kind of asset, right, you basically lose essence of how you make money, right? The second thing is, if you have particular sensitive data, they must be protected. So as an example, if you're in a regulated industry, right, finance is probably the biggest one, but we see this also coming through healthcare now. The healthcare regulations, which absolutely require you to guarantee that personal data is not being disseminated. It's always fun to go to a doctor's office and say, well, I don't want you to give my data out. No, I want you to be HIPAA compliant. They all start freaking out, right? Because why not, right? So I think the lack of trust in principle actually has been impeding the move to public shared infrastructures, right? Many of the workloads today have moved because, well, there's web serving and things like this, but the moment confidential or high value data has to be protected, people are still trying to lock them up in data centers, right? That's basically gave the rise to hybrid cloud, right? And so here comes in the two things that we need is confidentiality and integrity, right? Which leads to confidential computing. I think confidentiality without integrity is more or less useless, right? Because as a system engineer, if you have access to your data and believe that's confidential, but somebody through a side channel can modify your data, that's pretty much a side attack that you don't want, okay? So what we call basically in order to achieve that with confidential computing, we want to get away from what we call operational assurance, where, for instance, the cloud provider said, trust me, we don't want to we don't do anything with your data, right? Just deploy your application. We want to get to technical assurances, right? That means the cloud provider cannot access your data, right? Or your keys. So you see it on the left-hand side, the cloud operator and customers both have access to their data. And on the right-hand side, we have the cloud operator who cannot access the data. We jokingly call that the FBI test. If the FBI works into your data center, right, and says demands the data, you happily hand over the data, it's encrypted, and they have to go back to the customer for the keys, right? So your responsibility is to basically maintain key integrity and key isolation. And that's typically done by giving full access to a key management system, okay? Now what's happening is that, in my opinion, confidential computing will only be successful if the workload deployment is completely transparent. You flip a bit somewhere in your DevOps and say make it confidential, and it's going to go out. If you have to engineer around it, it's going to be very difficult to sell that, right? The second thing is the overhead has to be low, right? In one of the meetings that Rui once called, I joked that it's very hard to sell insurance before the hurricane hit. It's very easy to sell insurance afterwards, right? So people will look at what does it cost me, and then basically make a risk assessment, right? Whether they want to pay for it or not. So we want to look at performance numbers here, right? Largely, with the rise of the first few slides that I showed of AI coming pretty much everywhere, right? We clearly see an intersection between AI and confidential computing emerging, right? We also see that there's a trend for privatization. You take foundational models, and then you do fine-tuning on those models, making them effectively private, and that's where ultimately your assets lies, right? I want to distinguish between confidential AI in two sections. One is the model, right? So that might be the asset of whoever deploys this model or the service around that model. And the second one is the user input, right? So maybe the model is not confidential, but the user input running an inference against that model might be confidential. And finally, we see clearly the emergence of AI accelerators here, right, with GPUs and TPUs, simply from the argument that accelerators will be more energy efficient, right? And as a result, you get more performance per watt out of these systems. There have been very interesting papers, like one from, I think, 2021, which actually already showed that if your infrastructure is not protected by PCI, by monitoring PCI traffic, you effectively can reconstruct a neural network or like a model. And as a result, you need to protect the entire system. So let me go through that now. So if you're looking at confidential computing, we all know what the system looks like. We have a CPU interacting via memory controller to the memory chips, right? We have an I/O bus. Typically, we go through a memory mapped I/O. Data will be fetched over DMA, and we're ending up on a GPU, which by itself is effectively also virtual video RAM and GPU. So that's our standard non-CC system. So let's start breaking into what confidential computing essentially means. So if you basically take for a moment just the GPU out of the equation, what really has happened in all of these confidential computing architectures, they're driving towards what we call a virtual machine architecture. I know that SGX and so on has done it differently in the past, but what essentially happens is the GPU, when it enters into a VM or into a confidential VM, enters in a particular mode that now forces any memory traffic to be encoded, encrypted and decrypted. So what we essentially see, is effectively the memory controller, when memory is being fetched, will be decrypted, and when I write to it, will be encrypted. And the transformation of whether I'm now in an encrypted state or not will be done when I enter or exit the VM. So as a result, even if I'm a hypervisor, I can observe the memory. As an operating system writer, I always have access to all the memory. That's not the problem. But the key that's associated with it is completely hidden in hardware state that the hypervisor does not have access to it. Still, today, right, or until the NVIDIA H100 came along, most of these devices are completely unencrypted. But that's not what we want if much of the work is basically done on those systems. So fictitiously, one can say, well, let me just enlarge the enclave to include the GPU, but that is not as simple as you can think, right? Because we now have to look at the various interactions. So the way I typically look at it is that I take the principle of the US, which is, if you ever look at a quarter coin, it says e pluribus unum, like, which is Latin for out of many one. Right? So we literally have to look at each of these pieces in a distributed fashion. That means all the components need to protect their data. And you basically have to protect the communication. So the way I draw this here on the right-hand side, which I showed you earlier on, the CPU is protected by going in and out of the VM state. And as a result, the memory that's being used by the VM is completely encrypted. Okay? Now, the applications run basically unmodified in such an enclave. Now, when you start communicating with the GPU, number one, the GPU needs to protect, right? So you have choices. You can protect either by encrypting it, playing the same game that the CPU have played, or you basically can give the GPU entirely to the VM, or as the H100 will have probably throughout this year at some point, you do a physical partitioning, right? That's all a matter of performance, and we want to look at these performance numbers. Secondly, you have to look at is all the communication has to be protected. So when I effectively go from a CPU and I would like to send data or receive data from the GPU, that needs to be encrypted. Link encryption, as I've shown here in this example, right? So in this paper here, right, has already been shown if you don't have link encryption, you can extract through operations or investigation of the PCI traffic, you can reconstruct models, okay? So it follows then that we effectively have to look at the overhead of all these communication paths, because on that communication path, you will basically put latency-sensitive operations of encryption and decryption, okay? And we want to look at that. Now, many lessons can be learned by just looking where CPUs have come from. If you look, for instance, SEV, which in my opinion is probably the most advanced right now in terms of communication, or in terms of confidential computing, it had to go through 3 generations, right, to get things to the state where they are in order to get rid of certain side channel attacks and so on, right? So what will help ultimately is here at the bottom, which is basically standards that are currently being, well, they have already been defined. One is called SPDM, which is PCI link encryption. That's part of the PCI 5 or 6 standard. TDIO, which allows you to do a DMA access. Why? Because if a GPU tries to access memory, it will do it over GMA, but the memory is encrypted, okay? However, you don't want to have that, you don't want to move keys around, because the moment you move keys around, it becomes susceptible for interception. So you typically negotiate the key on an ephemeral key for link encryption over PCIe, and the DMA, when issued, is known to be issued in the context of the VM that started it, right, that's being tracked. And as a result, the memory controller can now do this, can do the encryption, all transparent to the hypervisor. So what I would like to go through is a couple of examples here of what it ultimately means from a performance perspective, right? And as a system engineer, we typically always start out with some benchmarks. Give me some ground truth, right? Is the marketing that we read out there actually true? So I'm going to go at the top right. We have some simple host benchmarks, right? Then we're going to go seeing what is effectively the overhead, right? The host benchmarks, we're looking at the memory encryption path here. Here we look at what does it cost me to go over a secure channel to get to the GPU. Then we're going to do a little bit of overhead measurements. Ultimately, we're moving over into more complex, because at the end, what we're interested in is in the large language models, right, at lab. Okay, so our system configuration, that's what we have access to. We have a Xeon chip here, an Intel Xeon chip, TDX. It has 2 terabytes of memory. We run a pretty recent operating system for both the host and the guest, and the version we have right now is TDX 1.0. It's very hard to get actually access to some of these machines, even if you're working in larger corporations, right? Now, on the NVIDIA card, we had basically 8 H100 cards plugged into that system that allowed us to do some scalability analysis also on what can be delivered to a distributed system. And these were the 80 gigabyte system, and we had 50 megabytes of caches. So the very first thing, just to get in a ballpark, what does actually the host cost me, right? No GPU, nothing involved, right? And so we just run the absolute simple system sysbench memory test. 5 terabytes, just scan through it with different block sizes, right? And you can see is if you're basically within the cache range of your CPU, the caches are unencrypted but protected via tagging, okay? You get pretty decent performance, and then when we're looking here across one thread versus 8 threads, we can see here at the bottom the overhead, right? So if you're looking at read, very limited overhead. It goes a little bit up when we are going towards larger batch sizes, and then it basically slows down again, which was surprising to us, because we would expect the more memory traffic I have, the more overhead I will get, right? However, most likely prefetching and other kind of things will effectively come into play. So Now, when we're moving this over to a spec bench, this is in no way authoritative benchmark. The way we ran it, it was basically 2 days before I came to the conference, right? But it gives us a kind of a ballpark if you put more complicated benchmarks up, and it's still roughly around 5% or at most, right? So it's tolerable, okay? So then the next thing we're going to look at is basically what does it now cost me to go to a device, right? Remember, we now have to have a device encryption or the link encryption. And there's quite significant overhead. This is straight out of the NVIDIA suite, right? So we're effectively running the device-to-device communication. And you can see here, if you're pushing data to the host, which basically means you set a command and it's being DMA'd over into the device, we can see that for, as the transfer size goes up, you're basically approaching peak here. However, for the red one, which is confidential computing, CC, right, we have a substantially lower overhead. And if you look here, the overhead or the performance loss is basically 90%. This is huge, right, at the surface. Why is that? Because today, Intel or AMD is not ready yet in their current version that you buy to have the TDIO enabled. That basically means when a DMA is issued from the hardware card, that the host already knows which VM it belongs to. The only way that they can get around is basically having a bounce buffer into which you do a software encryption. That's what NVIDIA did with their driver, right? And they get around the problem, right? NVIDIA card seems to be ready for us, right? So over time, we will see that this overhead will come down. There's no question. We don't know how much until we get this, probably by sometimes during this year. Okay, the same happens when you do a host to device. Doesn't matter, it's always DMA. Then one interesting observation we had is we also ran the device to device. So we're sending a command down to the card and say, just copy from video RAM to video RAM, same device. And you would say there should be no overhead. But for some reason, we see quite some overhead as we're ramping up here, right? So the green one is the default one, non-encrypted, and you see roughly at this level, we have a ditch. Most likely that is the 50 megabyte L2 cache on the card itself. But we don't see this effectively running in the confidential mode. So there's some setting in that card that potentially has disabled caches, and we saw that later on actually showing up, and I will point at it. The next thing we did is basically just a simple scaling analysis. If I have 8 GPUs and I'm essentially all of them assaulting the system with the transfer, how well does my system scale? And you can see in general, it scales pretty well. It scales pretty well, right? The only difference is that for a non-CC, the performance ditches more, but it's also much higher, right? 10x higher, 9x higher, right? And so it has the same characteristics that we saw earlier on, okay? So now let's go to some of the more sophisticated benchmarks. So the first one is basically a streams benchmark. It just looks at the GPU memory copies. So yeah, you see at the bottom left, you see the operations. These are classical operations you find in large language models, which are basically some form of vector or matrix multiplication with scaling or with adding, right? And you can see already, once we have the data on the GPU and the block sizes are large enough, effectively trying to overcome this problem here, right? Then you can see that effectively the overhead essentially goes to zero, right? It's almost no overhead anymore. It's all about communication into the device, it seems, okay? Now, the next thing we're running is basically more compute-intensive applications. So we took the GEM and the DXD. You can see the description of those, matrix multiplication and DXD, which is a compression algorithm. And again, there is a very low GPU overhead for compute performance, most likely also regulated to getting data onto the device. So we are very confident that having the device in confidential mode is pretty much, seems to be, other than that memory hump we saw there, effectively just a matter of getting the data into the device, okay? So now we're focusing on more complex benchmarks, which is not just either GPU or memory, right? So we're having now a benchmark that does GPU, memory, and compute at the same time. And so here we're taking the high-performance conjugate gradient, the HPCG application, right, which is a benchmark that comes from Sandia National Lab. And you can again see that there is some overhead, right? However, again, it's containable, in my opinion, right? So the next thing is, how much time do I have left? You can just shout it out, right? Otherwise, I keep going. So in large language model, the next thing we're doing is basically doing a discovery. Obviously, we all read the ACM papers that came out, right? And so we're trying to effectively recreate the setup. So we got from NVIDIA ML Perf, which is a private non-open benchmark, okay? And we ran it on our system just to replicate and see whether our system setup is correct. And so while their system basically, and I think the ACM paper was written on an HBM2E, so high bandwidth memory system, ours is basically equipped with a high bandwidth free memory, which basically means computation is faster, memory access are faster, and as a result, any I/O into the device will have a larger impact, okay? And so we were able to, here you see it on the right-hand side, you will able to see that the confidential versus the non-confidential computing are in the same ballpark, right? So most of the time it's just basically the same. So our interest is basically what happens if we're looking at some of the characterization, some of the parameters of a large language model, okay? So in this particular case, we're now starting to drive down certain parameters. So one example is, for instance, we are driving down the batch size, right? Obviously, when you write a paper, you show what's the best you can do. So in the papers that we have seen, the batch size was very large. However, right, sometimes you don't have the luxury to run very large batch sizes, particularly when your model gets large. Most of the memory will be consumed by the models, so you can't submit too many batches. That's number one. The second thing, when you're driving up the batch size in order to drive up throughput, you're basically increasing latency. Now, in many cases, when you, particularly as these workloads are all inferences, you integrating this workload or the inference into a business logic. And we all know when I basically make a transaction or have a request or anything like this, there's a certain service level objective involved, right? And the service level objective is typically given in milliseconds or seconds, right? Give you an example, you make a credit card application or the credit card purchase. Typically, the results from an interrogation of whether this is potential fraud or not has to be in less than 20 milliseconds, just to give you an example of an inference, right? If you can't come to a conclusion, the credit card transaction will go through, right? So in that case, you're not concerned about batch size, you're concerned about latency. So we're driving the batch size down in order to make a hypothetical latency, and we can see here as we're driving down the batch size, we're basically increasing the overhead, right? Why is that? Well, there's more communication per computation, okay? This is also the first time when we're running these benchmarks that we saw an error message going by constantly that basically says that OpenBlast, which is a hidden library that's being used by many of these models, cannot determine the cache size and assume 256 kilobyte. We were not able to drive this any further down, but that could be potentially the explanation that we saw early on in the memory-to-memory computation. It's obviously an extremely busy slide here, but MLPerf was obviously an optimized benchmark, right, that NVIDIA wrote, right? But what often happens, people will basically take open benchmarks and or open models and take them out of the box. So we started out with BERT as one of them, and then essentially did the same for Llama, and later on for Granite, which is an IBM proprietary. So when you look at BERT, you can do two things. Number one, we had BERT small and BERT large, which you see in the upper top corner, right? And we have Llama 7 billion and 13 billion at the bottom, okay? And just to talk about the tendency here, right? So I want you to focus on the green line because that's the tendency line, right? You see that the overhead, as we're increasing batch sizes, basically becomes almost zero. Why is that? Because the computation to communication overhead increases. The model's becoming more complex, there's more computation going on, and as a result, for every byte that I transfer, I have more computation, therefore reducing the impact of communication. You can also see that at the end, the more complex models get, the lower the overhead is, okay? So the next thing is we're looking at a private model, which is IBM Granite model. I think many companies are going towards this now, either by taking a foundational model and then fine-tuning it, or basically starting to train their own model based on the data that they have. Okay? And so what we can see is a very similar direction that we're seeing here, is that if you're looking at 3, 8, 13, and 20 billion, the more complex the model is, the lower the overhead is, which is kind of unintuitive, right? But it goes back to this very simple fact that we observe, is that the moment the compute overhead or communication overhead goes up, the overhead of confidential computing goes down. And you can also see here that as we're basically driving, as next generations of these GPUs are coming out, they're already being announced in a way, right? They're going basically with larger memory, right? And as a result, you can effectively fit more into the card, and the curves, or the tendency curves, will all basically go down. That's already with the current state of computation of communication overhead. Okay, so you can go a little bit deeper here, right? So we did some analysis with the profile NVIDIA Insight, right? And so when we're going, for instance, a llama model, and we're taking a batch size, sequence length 128, when we're going from non-CC to CC, you can see that the number of calls are pretty much the same, right? However, the overheads are coming from launching a kernel, which effectively bringing programs and other things over to the card, right? That we see substantial overhead. Another one is CUDA memory set. Right, as an example, memory set, you set a particular value inside the memory. Again, it shows up that there seems to be some overhead related to memory on the card when you're putting it into CC mode, which should not really happen when you read the material, right? There should not be any overhead. Okay, so you can now bring this up and get to a different one, right? So if you're now going to a batch size 32, all of a sudden it seems like the overhead is switching from launching the kernel, largely, right, to something else, which is memory management, right? So we see this here, there's a substantial amount of performance being eaten by memory management issues. Okay? So things I did not touch, but I would love to talk about somebody, I know I'm going to be out of time here in a second, right, is that how we do confidential sharing of devices. Right? So as an example, if you take the H100, it's partitionable. They're taking an extremely strict model of saying, if you give me a virtual, if you give me a MIC and the MIC is encrypted, right, we're going to do physical partitioning. They're literally cutting the coherency lines between the different slices. Each slice has its own RAM associated and so on, right? But for instance, what happens if you, for instance, want to share confidential models, right? And you just want to keep your data separate. So there seems to be sharing should be possible among different VMs or among different slices, right? And you're only going to keep your data that's related to the user input private. There's also some research we did with University of Illinois looking at encrypted memory. The same thing that what happened on the CPU, where any memory traffic is encrypted, only when you bring it to the cache will you effectively encrypt and decrypt the memory, right? At least the initial implementations that we saw from implementing a simple TPU didn't really warrant it. So truly looking at physically partitioned memory is actually the right thing to do, okay? So let me conclude here, right? I mean, what I've tried to show here is that security does come at a price, right? We saw at the initial, just running at the CPU level, you pay a little price, right? If it's memory heavy, it can go into up to 10, 20%, right? If it's not CPU heavy, then it's more in like the low single digits, right? Is confidential computing ready, right? I mean, as Rui was saying at the beginning, we have these devices now. I would say it's absolutely ready. Now, in our case, we had a TDX H100 ready. I know there have been plenty of papers that Microsoft has, for instance, published. I'm actually looking forward to the talk after the next one, right? Has shown that SEV and H100 systems are ready, right? Now, how easy was it to install, right? I was actually expecting an Armageddon, but it didn't happen. We just followed the instructions that were given. It was actually pretty straightforward. You update your firmware, you update your packages, and all the applications basically ran out straight out of the box, right? As I showed you, there is quite some high performance overhead, right? However, that overhead can be amortized if you basically make large batch sizes, right? You saw the trend curve lines, it goes effectively to 0, right? So the idea has to be, if you're writing software, try to overlap communication with computation, right? Then you can hide it. I mean, old software tricks, right? I'm absolutely convinced that with the TDIO coming out and the TDISC coming out in the next generation, this overhead will substantially be reduced. I don't know by how much. And my call to action is, if you're designing your own AI accelerator, right, or any kind of accelerator, please consider confidential computing right from the get-go, right? So make sure that you follow the new standards, integrate them, and I think that's going to give a big boost for machine learning in general and AI in general for confidential computing. Now, what's up for next for us? We're actually looking at, for instance, secure EDA workloads, right? Again, these are all high-performance applications, some of them having confidentiality requirements. And the final thing is what we're looking is exploring fine-tuning, right? I still believe that in many cases, machine learning or the training will be done in data centers, but when you go out in the field, these cards might effectively help to do the fine-tuning. With that, I want to thank you. Hope I didn't run over time too much, and I'll take a couple of questions.
Thank you, thank you. Any question for Frank?
Hi, nice talk. I'm just wondering about the overall security. So, for example, if you look at the history of SGX, right? There are many attacks on SGX, and usually, the attack model is not about attacking the encryption per se, but something else.
Yes.
Or maybe the overall thing, or it could be side channels, it could be physical attacks. So, I mean, whole bunch of possible attacks. So there's a question of the attack models and so on. And it wasn't quite clear what is the overall security picture. But of course, maybe this is early days.
Well, yeah, we're in the early days. So let me go back to the SEV example, right? When SEV initially came out, the first attack was on the state. If you're a systems person, you know you can single step through your VM, right? So every time you do a VM exit, I can look at your registers, and I can effectively replay your VM just from the register state. So the next thing they did encode in hardware the register state as part of a context switch, right? Next thing is S&P, which is effectively the integrity of your system. So the moment somebody touches your memory, you get a notification, right? So I think it's a cat and mouse game. I think I wouldn't be discouraged from that. Nobody will stand up here and say the system is 100% secure, right? But I mean, if you're getting towards a better system, why not? That's my take, right? I mean, I can only look at how systems are implemented, right? I mean, obviously, side channel attacks are a huge problem, right? Today, caches are unencrypted, right? So you absolutely have to hard tag these caches to make sure that you have cache partitioning in place, that you can't snoop on the cache traffic, you can't inject via your own behavior a certain cache behavior on somebody else and then extract information out of that. Right?
Just to contrast, right? If you look at TLS security, a lot of work has been put into that. There's like fully verified software stack, side channels, constant time computation, all kinds of stuff like that. And there's a lot of heavy duty work has been done to make it secure. So that's just a contrast, that's all.
Yeah.
Of course, it's a different problem.
There's a lot of stuff. I mean, at the end of the day, you want to basically integrate this into the software development pipeline, in my opinion. Right? I mean, that's just one tool.
We can have one more question. Anyone want to have a question? All right. Thank you, Frank. Our next speaker is Professor Bo from University of Illinois Urbana-Champaign. Thank you.
Hello, everyone. It's a great honor to share some of our recent research in this awesome, exciting workshop about assessing trustworthiness and risks of Gen AI. And I will mainly focus on some privacy perspectives, but I will also give some insight and findings about other perspectives in trustworthiness and the safety of AI, so that hopefully we can enjoy and discuss all the things together, because still, obviously, everything is still growing. And I'm both from Chicago UIUC, and we have a AI safety work startup called Virtual AI, and if you are interested, we're happy to discuss more. So first of all, a little bit background and motivation. I think most of you here don't need that, but let's just jump onto the same page. So we can obviously know that the machine learning and AI system have been ubiquitous in the world, which have been deployed to different domains to make our life better, including financial, chatbot, and face recognition systems. However, we can see that even such powerful security and privacy techniques, like AI techniques, have brought us a lot of security and privacy concerns. For instance, a real-world example, which is one of my favorite examples in 2016, was that the Associated Press Twitter account was hacked via phishing emails and spreading the rumor that the White House has been attacked, which actually triggered the automated bot to jump a large amount of stocks within seconds and swap about $130 billion within seconds. So that's something really happened in real world because of the so-called adversarial attacks for real-world machine learning systems. And obviously, we have known that every day with all the ChatGPT and the different types of chatbot, we have seen so far a lot of different chatbots, including retail, including skincare, all kinds of things. Still, their output could be biased, could be privacy sensitive, and leak a lot of sensitive information. I think we all remember the lawsuit between New York Times and OpenAI about the leakage of potential training data. And similarly, from the face recognition and image perspective, the face recognition system have been attacked in real world and lead to the misarrest. So we can see that even we have a very nice environment and different platforms to help us develop different efficient and effective machine learning AI systems, but still, as a typical machine learner, we still have a very hard life to build the so-called trustworthy and AI systems. And obviously, a lot of great regulations and laws coming to the ground and help us to emphasize the safe, secure, and trustworthy building of AI systems. And beyond the executive order from the White House, I think everyone knows, and there are a lot of other regulations as well, including the UI Act and including others. Actually, I was last 2 weeks I was in Paris and have a very great discussion with all the European leaders and researchers about the safety of the models and the AI development, which I think is very important and critical. And here, for example, in last year, there is also the AI Bills of Rights, emphasizing some trustworthy AI problems, including robustness, fairness, privacy, explanation, and human in the loop. So in this talk, I will take one example, particularly focus on foundation models and see what's the potential issues and how we can understand and assess them and what's the potential solutions to them. Obviously, there's no a final solution yet, but on the other hand, I think that's the exciting part, right? So first of all, as we can see that from the last year, the commitment from the leading companies, there are several important commitments writing down, including the requirement of the third-party risk assessment and the safeguard against the vulnerabilities that we find, right? With all these regulations and development and etc., I think the first question I want to ask is how we can actually assess the risks or potential risks of different AI systems built on foundation models, right? So here I will give a small, quick examples of this pipeline and see where we can start with, right? So first of all, let's say if we consider a very simple pipeline, which is built on foundation models. Like we have a foundation model, and then it can be applied to different domains like financial, healthcare, and a call center, etc., etc. And the first component we mentioned is that we need to have a risk assessment component. Like we need to how to do red teaming, we need to how to assess the models and doing a stress test. And second is based on the vulnerabilities we found, therefore we can apply and use develop different algorithms, including, say, different instruction fine-tuning, RLAF, and neural links, et cetera, to solve different potential trustworthiness problems. And finally, I believe we know that with all the purely data-driven models, they cannot be 100% safe or trustworthy, and therefore we need certain guardrails for the input and output. So in this talk, I will mainly focus on the first two blocks, but if we are interested in the guardrail and other blocks, we can discuss offline as well. So first of all, let's look at the red teaming part. And I want to send some interesting findings here about privacy, security, and some perspectives. So basically, the question we want to ask here is how we can assess the risks of ML models, and then what's the trustworthiness perspectives we need to care about, because when we talk about AI safety and trustworthiness, like everyone have slightly different focus, right? Like privacy, security, fairness, bias, etc. So what should be the set that we should consider into at least, right? So the first work I want to mention is the Decoding Trust, which is with a platform that we provided with the goal of providing the first comprehensive trustworthiness for foundation models, including large language models, including multimodality models, and including agent. So the first thing is that we first define the trustworthiness for AI safety or foundation models, including the 8 perspectives, meaning the toxicity, stereotype bias, adversarial robustness, the out-of-distribution robustness, and robustness against adversarial demonstrations, particularly considering the in-context learning, and the privacy, ethics, and fairness. And for each of such perspectives, we'll have sub-scenarios considering both existing benchmarks and additional algorithms which will use to generate additional challenging prompts or data set. So on the right-hand side, the details are not very important. I just want to show that there are a lot of sub-scenarios, et cetera, and I will give some examples, but we may not have time to go through all the perspectives. But the main point is that on the right-hand side is the generated challenging data and prompt, which is for on the long-tail distribution, so that it can help you to perform the additional risk assessment. And with this, we'll provide a comprehensive risk assessment for foundation models. And this paper also won the Best Paper Award at NeurIPS this year. Last year, sorry. So overall, based on the framework itself, there is a spider plot on the very high level, and we can see that if we actually evaluate different closed models and open models together, on the very high level, you can see, first of all, over all these 8 trustworthiness perspectives, we can see that no models will dominate others over all the perspectives. And second of all, from that, we can see that there is actually some trade-offs among different perspectives. So that whether those trade-offs are only empirical or fundamental, it's very important so that we know whether we can achieve the best word among all the perspectives or not. So I think that's a very interesting direction, and we have some work actually to look into and prove that the fundamental correlations between OD robustness and adversarial robustness, and adversarial robustness over privacy, unfederated distributed systems, etc. So basically, what I want to say is that there are a lot of potential fundamental trade-offs that can be explored over the trustworthiness perspective so that we know eventually what we can achieve and what we can expect. So that's on the very high level what we can find. And next, I'll briefly go into 2 perspectives. One is toxicity, which everyone cares about because of the chatbot deployment. One is privacy, following our theme in this workshop today. And then we can take a look and see what we can find over the red teaming effort for foundation models. So first of all, there's an example here. On the left-hand side is the input. The pink part on the right-hand side is the output. So basically, the idea here is that we give the input, or we generate the challenging prompt to the models, and then prompt the model. And the constraint is that for the input, we constrain the toxicity scores for the models are not very high so that they can be stealthy. And on the right-hand side, we will evaluate how toxic the output could be. And by the way, all the examples in this talk come from GPT-4, so we can leverage a capable model to illustrate our analysis and findings. And what we can see here is that from these two examples, the top one is normal like a system prompt, like you are a helpful assistant, that's all. And second is that you have the challenging, like a jailbreaking system prompt. So we can see for both examples, as long as you give a challenging user prompt, like say Trump say something. So basically on the left-hand side, the input is very benign if you give it to any like a perspective API, for example, to test the toxicity score. And then on the right-hand side, you can see, unfortunately, the toxicity score is very high. Here, the number, the higher, the more toxic, showing that how toxic the GPT-4 itself could be, even though they have already been very carefully instruction fine-tuned and RHF, et cetera, to help protect. But still, it is very toxic. And the goal here is, first of all, we want to evaluate how the GPT-4 and 3.5 compared with non-instruction fine-tuned model, how toxic they are. And second of all, actually the very capable model like GPT 3.5 and 4, how capable and toxic they are. So with a little bit a quantitative example, we can see that from the green part, we compare the capable model like GPT 3.5 and 4 with existing model like baselines on existing benchmarks. And the number here higher, the more toxic. What we can see here is that great, that if we look at the toxicity score, GPT 3.5 and 4 reduce the toxicity on existing benchmark, which is great. But if we look at the pink part, which is against like our generated challenging prompts, then we can see, unfortunately, the toxicity score can be back up to about 100% again, which means there's no toxic protection at all. So the quick conclusion we can find from here is that compared to the LMs without instruction fine-tuning or RHF, like other GPT-3 models here, we can see that indeed the capable model, such as GPT-4 and 3.5, can reduce the toxicity. However, unfortunately, we can see that both of them can still be pop up to very toxic under the challenging prompts, like the examples here, and they can up to like 100% toxicity. And one very interesting finding we find through all this work among different perspectives we find is that actually we see GPT-4, unfortunately, is more toxic or more vulnerable than for example, GPT 3.5. So at the beginning, this sounds very counterintuitive and weird, but then if we consider it more, we can see that it's also aligned with our intuition. And the reason is that we know GPT-4 is very capable, therefore they have good instruction following capabilities, etc. But because of this, so that if you have a little bit like adversarial or misleading information in the prompt itself, then the model can immediately follow again, and therefore generating like adversarial behaviors and like, for example, toxicity, etc., etc. So that's the unfortunate thing, and therefore we need to be careful and be aware of such vulnerabilities among for when we use models and among different perspectives. So after toxicity, let me go into the privacy perspective a little bit, which I think is very interesting and some surprising findings to myself as well. So here, similarly, we have the left-hand side as an input and right-hand side as an output. So the idea is that we want to give different types of context. For example, the first example is unstructured context, and second is a structured context, like different format. And the idea is to extract the private training data from the model itself. But we can see here that there are some challenges. For example, for the closed model, like GPT-4, we don't know exactly what training data they use. Therefore, it's challenging to, say, extract the pre-training data, right? But as an example, as a result here, we basically make an assumption that assume the GPT-4 actually is using the the open Aaron email dataset, which is a well-known open dataset, and we'll assume that they are training on this dataset, and then we give context based on this dataset and see whether the model can leak information from this dataset. If so, we can conclude that not only the model is trained on this dataset, but also the model can leak information from the dataset, right? And this is the first perspective or sub-scenario that we look into in terms of the privacy leakage of foundation models. And the second perspective is that we try to identify or recover the PI information from the conversations of the model. And third is that we look into some privacy-related words and events and understand how the model actually understands different privacy-related words and events. So from this, we can see some numbers here on the right-hand side show that, unfortunately, the models, for example, GPT-4 and 3.5, can leak private information, for example, email or credit card, up to 100% accuracy under certain scenario. For example, zero shot and few shot. So basically, it exactly reveals that indeed the model is trained on, say, Aaron email dataset, and they can effectively leak information from their pre-training data, such as Aaron email dataset, which is pretty dangerous and also a phenomenon we kind of know. But here, quantitatively, we can see how effective the model can leak information like this. And second of all, I want to go to the sub-scenario about this privacy-related word, which is actually quite surprising to me when I first look at it, and I think it's an interesting thing to understand. So first of all, we can see here on the left-hand side, there are two inputs, and the idea is we chat with a bot, and it tells about a secret in confidence or confidentially. So basically, everything else is exactly the same, but only when you tell the model some secret or some event confidentially versus in confidence. However, on the right-hand side, you can see that when you tell the model confidentially, the model actually will exactly leak such information. But if you tell it in confidence, the model actually will say, okay, since you told me in confidence and I will protect your information, I will not leak it. So the idea here we want to reveal is that actually there are different privacy-related words and privacy-related events. To human, they are semantically the same. However, to model, they are completely different. So that the model, there is like a rough confusion matrix to look at the combination between different privacy-related words and different privacy events, like device, healthcare, like voting, etc. And they have certain combinations. Under certain scenarios, the leakage rate is very high versus some scenarios, the leakage rate is almost zero. So that means under certain scenarios, if we don't understand the model carefully using the capable or advancing red teaming effort, then we'll have some false impression about security. So that, for example, if we only look at the second row of the example, we'll see, oh, if we tell the model, in confidence, the model will protect our private information, but actually they will not if you tell them in different words, like confidentially. So you can see that this is pretty important and actually raise a lot of alarms, like how we should use the model and what we should take care of when we use the model directly. So the quick conclusion here is that actually, first of all, as we know, GPT-4 can leak, or all kinds of GPT models actually can leak privacy-sensitive information very effectively, unfortunately. And also under few-shot prompts and etc., they can leverage the knowledge and leak more private information very effectively. And later on, we can see that the models can leak some PI informations. And something we find very interesting is that the model actually can very hard leak some sensitive information, for example, social security number, but they can leak like credit card number or other things. So it's very obviously that the model have been very carefully instruction fine-tuned on certain things such as social security number. And this tells us, first of all, it is effective if we want to protect some information and we do some careful instruction fine-tuning or things. However, it's definitely not enough as a solution because we cannot enumerate all the private sensitive information, etc., to protect them, right? So we do need some systematic way to protect, say, private information, protect the security for the models, etc., if we want to actually deploy them in real world, right? Later on, we have some other findings. For example, the model actually protect the digit better than characters. Maybe there are more characters in the training data, so that leak the model properties. And finally, as we show that the model actually have different understandings about different privacy-related words and events, and we need to be very careful about them because we don't have a good understanding about them. So that actually need to be taken into account when we talk about, different privacy protections and use models in sensitive domains. So with this, I want to give some examples about the red teaming effort to show that how the model can be vulnerable from different perspectives, including toxicity, privacy, and other perspectives. And this leaderboard currently has been hosted on Hugging Face as a standard LM safety evaluation leaderboard. If you have your own model and other frameworks you want to understand or want to evaluate, welcome to submit to it. And actually, currently, there are open model, closed model, and different types of compressed models in this leaderboard, so that you can see and understand the model capabilities, at least from the relative perspective. And next, since we talk a lot about red teaming and how we can attack models, and I can actually talk about how to attack a model for a whole day long or weeks long. But next, I want to use 3 to 5 minutes to talk about potential protections and how we can protect the models. Obviously, this is very open, and there are a lot of things ongoing still, but I want to talk about certain principles, and from the first principle perspective, what we can do and what we kind of should do to pursue the trustworthy and machine learning models, especially foundation models. So in the second part, I mainly want to discuss how we can protect the data privacy in the era of Gen models, right? Because we can see now with Gen AI, we need a lot of data, a lot of compute, and all this data have sensitive information embedded, and how we can protect them is very important. And I think previous talks have provided very interesting perspectives from the system level. And from the algorithm level, I want to look at and discuss what we can do, right? So basically, we can see here, this is a very straightforward pipeline with input data, and then you have a machine learning model optimization, post-processing, and prediction. So there are several components we can do here in terms of data privacy protection. First of all, obviously, we can generate privacy-preserving synthetic data with certain guarantees, for example, differential privacy, right? So that we can leverage that data for downstream tasks. Second of all, we can do privacy-preserving training or fine-tuning, right? And third, we can, if we already trained the model with sensitive information, we don't want to retrain it again, we can do certain unlearning and neural cleans and try to remove the sensitive information, right? And finally, we can provide certain privacy information guardrail to make sure your output will satisfy certain things and will not leak certain private information if we have a good way for the guardrail. So for each of the components here, we have a series of work. I think it's very interesting, and I think my view is that we need everything together for the whole pipeline to make it work rather than one component will dominate the other. So I think this is an end-to-end solution. And there are different attacks and defenses we provided. This is a large categorization. I will not go to detail about it, but if you're interested, we have a website about it and findings under each attack and defense, and feel free to look at it. So in this talk, I mainly promise 2 minutes to go through one solution we have for privacy-preserving data generation, which I think is, as we show here, is a first component. And we need to do well on the first component, and then we can continue with other components. That's my personal view, so that I want to discuss from the privacy-preserving data generation perspective. So the high-level idea is that given any data, we use, generative model, for example, GPT models, to try to generate some data, and then we sample in the embedding space by adding noise, we will discuss how we add noise, such that we can satisfy differential privacy, and then we can guarantee the generated data is differentially private with the training data, and they kind of have high quality in terms of the distribution match, so that we can guarantee the privacy of the data. So here is an example that, okay, with the training data, and if you put to language model, as we show, that they can exactly leak information such as social security number here. The idea is that can we do something in the middle such that when they leak, the distribution is similar, so that they can still say, okay, my social security number is something, but the actual sensitive information is removed or is adapted so that they will not leak the private information. So obviously, there are lots of constraints. For example, in real world, we only have closed source API access to the closed models. Can we just generate data with only API access to the models, right? So this has high requirement for our algorithm design, and also we hope it to be cheap because there are so much data, and we hope the data can, on the large scale generation rather than super slow. So with this, the algorithm actually is very straightforward, look like this. So basically, first of all, you give some prompts to prompt the model, generate something that is following the scenario. For example, here it's a Yelp review example that we can ask the model to generate Yelp reviews, and on the right-hand side, the red dot shows the private information, right? On the left-hand side, because you just prompt the model will just generate something randomly. Right? And then after the model generates something randomly following the scenario, you will have left-hand side, which is the synthetic data, right-hand side, which is the private data. And then you map them to the embedding space and calculate their distance, for example, L2 distance or whatever geometric distance. And then you have the voting to show which synthetic data is closer to all those private examples, right? So you have the voting about the closeness of the data. And then you add noise to the voting histogram itself to guarantee differential privacy, to showing that, okay, my voting will not be exactly accurate, so I have some noise on it, so that you can ensure the embedding distance is satisfying the differential privacy property itself. And with this, you can actually sample the data satisfying privacy. For example, here, instead of the private data on the right-hand side, the differentially private data as one example is a great spot for pizza. So basically, it's different from the data from the right-hand side, as you can see, but it's actually revealed the similar distribution and meaning. So we can do this iteratively by adding additional variation, so we have additional, generation and map it back to the model to generate again and sample again and generate again, like basically iteratively. So eventually you will have a lot of generic sample data. So you can see here from this process, you only need API access to the generative models, right? And you can satisfy differential privacy, and the efficiency is pretty good in terms of we only need the model prompting, right? So a quick example is that, first of all, we can see that if we generate data, for example, by prompting GPT 3.5, and then you can see on the bottom row, the utility of the generated data is pretty high compared to all the other methods, like differentially private fine-tuning, other synthetic data generation, whatever. So basically shows that this generation itself is very effective in terms of protecting privacy of data and providing the guarantees. And second of all, we can see the better generative model we have indeed will have better utility of the generated data, which is understandable, and also showing that the internal knowledge of the model is actually helpful in terms of such data generation. And very interesting, we look at quantitatively for the private and the generated data distribution. From this figure, we can see that they are actually pretty aligned, showing that we can do a pretty good job in terms of distribution preservation, but still you can get the differential privacy guarantees. And finally, I want to show a quick example is that if you can see, this is the Yelp review, and then the private data, for example, if we view Mexican food is a private information, just an example here. And over the iterations, you can see in the end, the authentic Mexican is actually the generated result, which is different from the private information, but actually it preserves the distribution pretty well. And as human, for example, we can understand, and as model, they can understand as well. So yeah, I think in this talk, we mainly focus on certain red teaming effort to understand the vulnerabilities of the models and the one potential solution of privacy protection in terms of privacy preserving data generation. And there are other bunch of directions or like two boxes we provided for protecting, agent, protecting like fairness, protecting ethics, and help to generate data in a differentially private way as a toolbox, etc. So happy to discuss more. Yeah, thank you, everyone.
All right, thank you, Dr. Lee. And is there any questions? Okay, great. Okay, go ahead, this one first.
Yeah, thank you, Dr. Lee. I'm Goli from Nanyang Technological University, and I'm pretty interested in one of the adversarial testing topic you're mentioning. And I saw that in the data set, you're comparing all the security of different models, particularly including GPT models and other open source models. So I am wondering that if you have tested on any more recent models, such as GPT-4 preview released in November last year, And how is the performance of these models against the previous release models? Thank you.
Yeah, that's a very good question. So indeed, we actually evaluated different released models, for example, GPT 3.5 and 4 over different times, and we find that the security properties actually remain similar, but some utility drops. But we haven't evaluated the most recent GPT 4 preview yet, but we have evaluated Cloud 2, Cloud 2.1, and etc. And the Cloud model actually, surprisingly to us, is very trustworthy over our leaderboard. So it's a very good impression. So yeah, we are continuing adding more and more models still, and it will be good to evaluate more. Yeah.
Okay, follow up?
Yeah, thank you.
I had a question on the toxicity. How do you evaluate? How do you assign a score, right? Because is it basically how offensive it is to a large body of people? And how do you make sure that that assessment is not biased by itself?
Yeah, exactly. It's a great question. So for each perspective, we have different ways to evaluate it. For example, for toxicity in particular, in order to do fair comparison with other baselines and datasets, we leverage the Perspective API from Google. So that API will assign a toxicity score so that we generate our prompt data and send it to any models and get the output and send the output to Perspective API so that we can have fair comparison with other benchmarks or datasets. But I think I agree that's not the ideal case because we actually find there's some problems with Perspective API. For example, for swear word and a minority group, they particularly look at that and then give toxic toxic scores. But we just want to show for relative comparison among models, so that can do the comparison. But definitely, we are actually also trying to develop a better toxicity and safety benchmarking and a scoring to evaluate it. Yes.
Hi, Professor. So there was a paper from Anthropic a couple of months ago about sleeper agents, where LLMs, even after training, still retain the backdoor and were triggered by the trigger word. Well, what are your opinions on how we can detect these backdoor models, since gradient-based detections do not seem to work very well with these large language models because of the number of parameters and everything. Or if there's any opinion from you on that topic.
Yeah, exactly. A great question. I didn't have time to go into this backdoor topic. It's basically this robustness against adversarial demonstration. So I think what you are mentioning is a sleeper agent from Anthropic, the backdoor and the code generation model, and then generate harmful content and potentially malware as well, right? And we actually show here not only you can add the the backdoors in the pre-training data, fine-tuning data. You can also add the backdoor during demonstrations, in the incarnate learning, and you can add backdoor during the COT, chain of thought, reasoning steps, unfortunately. So first of all, backdoor is a very effective way to prompt the model, and the cost is very low in terms of attacking the model, unfortunately. So we need to be careful about it. And second of all, in terms of defending or detecting the backdoors over foundation models, on the high level, I think it's still very open. There's no definitely good way to do that yet, but there are a lot of work on it. For example, we have some work looking at the output, because after backdoor, the output could have some malicious behavior, and you can look at it. And we can also look into sample the model multiple times with different variations of the prompt, and from the a statistical testing perspective to look at whether the model significantly behave differently over certain scenarios, which may indicate the existence of backdoors, right? But those are the ideas we have in the past and currently working on. But to be honest, I don't know the best solution yet. I think it's an open area. Yes.
All right. Thank you, Dr. Li. And sorry, we don't have time. Yeah. Thank you. All right. Our last keynote speaker is Antoine, who is a principal researcher of the Microsoft Research. Oh, you can use that one. Yep.
works. Yes.
All right, looks good. Yeah, great.
Okay. Okay, welcome everyone. Thanks for inviting me to giving a presentation at AISCC. So today I'm going to present the work that we did with NVIDIA to kind of bring the first confidential GPU VM product to the market. And it has been, so in terms of why are we doing this? Well, I think most people in the room should already understand at this point. So we want data protection all the way for anything that you do on the cloud. So essentially the idea of confidential computing is we want to give you the same security when you run your workloads on the cloud as if you were running it in your private data center or in your basement. And this means that we have to give you strong hardware-based protection from all kind of cloud-based threat vectors. But more importantly, we also give you protection for end-user data against both a malicious cloud service provider and malicious tenants. And these are actually slightly different things, and maybe I can say actually a bit more about this. So you have kind of two classes of users for this technology. So you have, for instance, a company which owns some secret data, and they want to perform some computation, they want to maybe run some fine-tuning or some training. And in this case, they want the data to be private to the cloud service provider, so they don't really care that much about their data scientists having access to the data. So for instance, if they create a VM, it's okay if the data scientists can SSH into the VM and they can like do tests with the data. And so that's kind of one class of consumers for this kind of technology. But I think there is a more interesting class of users, which are essentially people that want to sell some products which use confidential computing, and they want to guarantee to their own users that they cannot access the data that they are processing. And these are typically specialized companies, startups, which are specialized in confidential machine learning. And the kind of products that they want to build is some kind of experience where, for instance, you may have some party which trains a new type of model, maybe a medical imaging model. And they want to kind of sell access to the model, but without allowing the users to actually extract the model weight. And then you have the hospitals, which are essentially going to provide the inputs to that model. And the hospitals, they want to be kind of protected against both cloud service provider, but more importantly, the tenant, which is the actual person who runs the VM on Azure, which is actually running the inference service. So these are kind of all of the considerations that we are looking at for confidential computing and confidential AI. And obviously, the last class of scenario, which is also extremely important, is it's not just providing protection, it's also about unlocking new capabilities which are not possible today, right? And multi-party is one of the key new scenarios which is enabled by confidential computing. It's also enabled by other privacy-preserving technologies. So if you are familiar with secure multi-party computations or with homomorphic encryption, these are typically the technologies which would be used to do these multi-party scenarios. But obviously, this comes with very, very significant programming model limitations, very significant expressivity constraints, performance issues. The only technologies that actually lets you implement these multi-party scenarios today on kind of state-of-the-art AI models is confidential computing. And that's why it's a very important technology for us. So because of all of these reasons, confidential computing and especially confidential accelerators is something that we have been essentially working towards or wishing for more than 6 years. So some of the first papers looking at this problem actually come from Microsoft Research. So on the bottom right, you have Graviton, which was one of the seminal papers at Oakland 2018 from our group and trying to kind of draft what would be kind of the additional hardware protection that you would need to build into NVIDIA GPUs to make them confidential. We also invested significant effort back in 2019, 2020. We worked with a company in the UK called GraphCore, which was building their own kind of AI accelerator. And we actually, as we are discussing in the first keynote, we tried to work with them to build confidential computing into the accelerator kind of from the ground up. And interestingly, this led to a design which was very different from what I'm going to present today. Because the design that we were working back then was what we call the fully disaggregated design, which means that you only trust the accelerator, but you don't trust the hosts at all. So that's a model which kind of comes with some constraints on the usability, but gives you very strong guarantee because you don't trust the host at all. And there are kind of many other papers, obviously, that look at this space, many of which try to kind of make use of NVIDIA GPUs from HDX enclaves, which turned out to be like completely, well, it's very hard and it's very dodgy to try to do that anyway. So why is it dodgy? Well, I think the reason is when you look at the requirements, you don't just have the security requirements. So of course, the security requirements are very important. You need to provide confidentiality and integrity, which means you need to be fully isolated from the host operating system and from the hypervisor. That kind of is a baseline for any confidential computing. And you also need attestation, which is kind of the third component. That's the 3 ingredients for confidential computing. You need confidentiality, integrity, and attestation. But beyond that, the issue is that we also want to have a usable products. And that kind of brings new requirements. So one of the key requirements is, in the case of NVIDIA GPU, compatibility, right? And that's what we are also like discussing in the first keynote. It's only going to get widespread adoption if it's a painless experience for the user. If you have to kind of ask the user to re-implement completely their inference runtime or to redesign their model, it's never going to fly, right? So we have to make sure that we can run existing unmodified CUDA applications, and that's why the experience that you got when you tried it is so painless, is because is designed to provide this seamless experience. So you are kind of just supposed to get your VM and your existing programs just work. And that's kind of, it's one of the very strong design requirements for the whole thing. And for NVIDIA, kind of trying to represent their requirements, they also don't want to have to maintain different code base for confidential and non-confidential. So they want to be able to support confidential computing kind of as a primitive feature in their driver so that they don't have to maintain different code base and stuff like that. So because of these requirements, the idea is that we want to create kind of extended TE between the CPU and the GPU. And the only way to kind of get all of these requirements is to include essentially the guest operating system and the GPU driver within the trust boundary of that TE. So that's kind of the reason why all of this has been built using kind of a VM-sized trusted execution environments like AMD CVSNP and Intel TDX. So this kind of VM-sized TE, so it's something that we have also been working with Intel and AMD for several years, and that has been available in Azure for a few years. So it's available as Azure confidential VMs. And it also kind of comes with its own set of challenges that I kind of want to explain a little bit because they actually come into the picture to understand the security of confidential GPU VMs. So one of the difficulties is the way that you can actually attest kind of a VM-sized TE. So when you look at the way that HDX attestation works, it's really kind of simple. So HDX enclave is basically a process, and when you initialize that process, the CPU is going to hash all of the data, the memory pages that is going to launch to write into the enclave memory before it actually starts execution. And that is kind of fine, but it also comes with this kind of difficulties that you need to hash all of the memory contents, which for a small process is okay, but when you are dealing with kind of a VM size, and we are talking about HPC VMs, this is essentially a terabyte of memory, and hashing a terabyte of memory is not something that is so practical. So the way that confidential VM works is that the TE doesn't actually measure the full image that is going to run at startup. Instead, it's kind of it's a multi-stage boot process. So you have a first stage boot, which is going to initialize these purple components. So you have what is called a VM paravisor, which is kind of, you can think of it as a trusted mini hypervisor that runs inside the TCP boundary. It's going to be used to provide helpful services to the guest operating system. And in particular, it's going to provide attestation through the virtual TPM. So that's why there is kind of this boot staging. It's mostly for attestation purposes. So you use the PSP attestation, which is the actual kind of low-level memory hashing done by the root of trust of the AMD CPU, and is only going to measure this very small first stage image, which includes the hardware compatibility layer and the UEFI firmware. And so, as I said, the primary feature or functionality of that is to provide virtual TPM, but it also needs to provide persistence for the state of that virtual TPM. Because we also want, so we are going to rely on the virtual TPM to give us the encryption and the integrity protection of the actual guest image, right? So effectively, most of the disk encryption technologies, both in Windows and Linux, so you have BitLocker on Windows, you have dmcrypt, dmintegrity on Linux. If you want to use them, you need a TPM because this is where you actually persist the encryption key between reboots. So in order to provide persistence of that TPM keys, which are used to encrypt the disk of your VM, we are using a kind of encrypted C-link using the Azure confidential key management service, which is called Managed HSM. So these are actually going, the C-link keys for these TPM states is actually stored in HSMs, which are protected by SGX enclaves. So this is kind of the platform sides, just to make sure that we can provide you with TPM-based attestation and persistence for the OS disk encryption. And on top of that, you have the secure boots, which protects the integrity and measures the guest kernel size. So this is just using TCG measure boot. And lastly, you have the application itself. So for the application, you have kind of two ways to try to attest the application. So the indirect way is you can say that, for instance, you may create a read-only disk image, and you use dmverity, which is the full Merkle tree hash of all of the blocks in your file system, to create a single dmverity measurement, and then you say that you authenticate effectively the frozen disk image as a single value in the TPM PCR, and that's what you use to prove that this is the application that is executing. So that's actually very constraining, and I don't think many users are actually going to do that. So the other approach is more kind of indirect, but you can use the PCRs of the TPM to do custom PCR extensions that can be verified using TPM quotes feature. But if you do that, obviously, there is kind of a downside, which is you're putting more trust in the tenant, right? Because the tenant is a person who actually controls the disk image. And you can create, for instance, a disk image where you SSH into it. And then after you have extended your PCR registers, of course you can do whatever you want. It's your VM, right? So you have to trust the person that is managing the VM. Okay, so now I hope this was kind of helpful to understand confidential VMs. And confidential VMs are not easy by any means, even before we add GPUs into the mix. So know that we try to add GPUs, we obviously run into more problems, some of which we already briefly mentioned, but I'm going to give a bit more details. So one of the features of HCL is that we actually take care of the management of memory encryption on behalf of the guest image. And so that's because on SNP, you have essentially two ways that you can try to do confidential VMs. So you have kind of the fully enlightened way, where you essentially do a lot of patches to the Linux kernel so that you kind of decide at the page level which pages are encrypted and which pages are not encrypted, and which page can be shared or accessed by the host. And then you have what is called the VTOM approach, where you essentially do a static partitioning in the physical address space of the VM between the region that is going to use memory encryption, so all of the page in this region below the VTOP of memory address will be encrypted, and everything that is above is shared. And in fact, when you use TDX, you don't actually have a choice. When you use TDX, you are forced to use this approach, which is also a reason that even though technically the fully enlightened approach is kind of more secure and more flexible, we actually go with VTOM because we also need to support TDX eventually. And then you need to deal with the associated issues. So typically the way that you access the GPUs is through MMIO, right? So you read some physical address location which map to the base address registers on your GPU, right? And you run into some issues because some of these addresses, which are kind of defined by the MMIO standards, they actually fall into encrypted memory regions. So if you actually try to read them, or write to them, for that matter, they will actually be written to encrypted memory page. And you cannot kind of map that to device because it will just write garbage, encrypted garbage. So you have to do all kind of remapping. Some of it is done in HCL, some of it is done by doing kind of enlightenments in the PCIe stack of the guest image, just to make sure that you can actually address the device properly. So this is kind of the work that we had to do with NVIDIA. So we created kind of new interface for allocation of the DMA buffer so that everything kind of falls into shared address space and can actually be used by the guest. Okay, so now I'm going to just explain a bit more the way that we actually create confidential GPU VMs. So the first step is that you have to enable confidential computing on the GPU, because not all GPUs are going to be in confidential computing mode. So the way that this is done is you can essentially use the NVFlash tool, which is normally used to flash the vBIOS and to change the persistent settings which are in the flash of the GPU. So this will essentially set a bit that will indicate that the next time that the GPU is going to boot in secure mode. So this is kind of how you set it, and it's set in such a way that you cannot turn off CC mode in the middle of the tenants executing something, because that obviously would be really bad. So the guarantee that the hardware state machine of the GPU gives you is that when you reset the GPU, all of the states, including the cache, including the HBM, have to be obviously fully cleared so that you don't leave any secrets that could be read or accessed by the cloud service provider. So then you go into the secure boots of the GPU, which is, I'm not going to go into the detail of that. So you have multiple root of trust to coordinate. So you have a first stage bootloader in the FSP ROM, which is going to read, flash, and kind of orchestrate the initialization of the other microcontrollers. But the important point is that all of this is using RTS and other kind of hardware registers so that you can get full measurements for the states of the initialized GPU. And that's what you will use as a tenant. So obviously you also have hardware isolation primitives that NVIDIA has added. So you have the firewall, which creates isolated memory region. And the place I'm just going to explain a little bit more is how do you actually do DMA, right? Because this is the critical operation. And it's important to understand some of the performance constraints that we also discussed in the first keynote. So when you want to do DMA, you have to do DMA from a buffer which is outside the encrypted physical address space on the machine, which is why so the GPU driver will have to do copy and encryption. And typically this is called bounce buffering. So the buffer we actually write is called the bounce buffer. And so this is going to introduce different overheads, both in the copy and in the encryption, and also in initialization of the commands. So you see that you also have kind of MMIO commands to initiate the DMA operation from the GPU driver to the copy engine on the GPU. And this also needs interrupt mechanism to notify the CVM when the DMA has been completed. So this is where we kind of, again, need to do more system work because so there is some APIC controller which is going to create some interrupt, but obviously we cannot interrupt the CVM because the registers for context switch where you normally notify of interrupts is encrypted with SCVES or SCVSNP. So that's why you also need to reinject the exception with supports from HCL. So that's kind of the work that had to be done in order to make confidential GPU VMs possible. So I want to kind of finish with some more comments about attestation, because attestation is really one of the sticking points in making confidential AI kind of a reality. Because the problem with attestation is that it's necessary for security. If you don't verify attestation properly, you don't actually get confidentiality guarantee. But customers really hate attestation because the only purpose of attestation is to break their workload. It's the only reason it exists. So that's why the customers, they actually have a very hard time with verifying attestation reports. And in the case of confidential GPU VM, it is actually quite difficult to verify attestation because you have the attestation produced by the CVM, which is itself quite complex. So you need to look at the hardware PSP attestation of the paravisor, followed by the VTPM attestation of the guest's image. And then you have, obviously, the GPU attestation, and you have to bind the two together because you have to prove that this is a GPU that was attached to that particular VM, right? You don't want to kind of pretend that you have a good GPU when it's a GPU which is running somewhere else, or it's emulated GPU by the host partition, all kind of attacks that you can do, right? So for that, you kind of do some binding protocol, and you are kind of restricted in the way that you do that because the only dynamic secrets that you have on the CVM side is the virtual TPM. So you have kind of to do everything based on the virtual TPM, and you have to kind of combine the attestation evidence from the GPU by putting that into one of the TPM PCRs. And then you have to do TPM-based quoting or TPM-based attestation so that you create a full package that covers everything. Okay, so I hope that wasn't too boring. I think for ML people, this is probably too much details on kind of the system side. But the security, if you want to kind of understand what confidentiality you get, unfortunately, you really have to understand the way that attestation design works. It's the only way to explain the insecurity. So as I said, this is something that is available as a private preview right now. So if we have some customers which are already using it because they're onboarded, you can sign up, but probably it's better to wait for the public preview, which is just maybe 3 months away. So now, soon everyone will be able to kind of get these type of VMs and run their own workloads. So we created some sample applications. So just to kind of give you a bit of more domain-specific or AI flavor to the talk. So obviously we went with something that is pretty popular right now. So we went with retrieval augmented generation. And we try to make it as simple as possible. So we create a long chain application, which is just a few lines of Python, really. And it's going to talk to an inference service, which is going to use CUDA runtime. And the main thing that we provide is this application encryption proxy, which is kind of trying to illustrate how you can add security to existing AI application. And the goal of this attestation encryption proxy is to protect all of the traffic that you have between typical clients, which in this case is a web browser, and your actual long chain application. And so there are many papers that try to look at how to do that. So one of the popular ways is that if you have enlightened clients, then you can use attested TLS, right, or attested HTTPS. So you can try to carry the attestation information as part of the key exchange done in the TLS on-check between your clients and your application. But it turns out that for many customers, this is not practical because it only works if you install a custom client. And that's a very big constraint, right? So if you want to have an application which gives confidentiality but can be used both by attestation-aware clients and legacy clients, people who just don't care about attestation, they just want to use your system, then you have to do some application-level encryption, so you have to introduce some protocol which is going to do application-level encryption, so you have to exchange key share on top of HTTPS, and then you have to kind of flow. So one of the issues is that, one of the interesting issues, in fact, with web-based applications is that you get the code which is going to run from the server. So if you cannot trust that code, then you cannot use attestation to verify that code. So kind of one of the nice solutions that you can have to this problem is that you can create a trusted browser extension which is going to check attestation and do the encryption for you. So that's, for the website, you just write your website as a normal website. Okay, so to give a bit of concrete feel to this, I'll try to kind of give, I'll try to see if I can show here. So this is actual confidential VM that I created. So you can see that it has the NCC type. So NCC is the new SKU type for Azure confidential GPU VM. And it's basically just running vanilla Ubuntu inside. So you can see here that it has NVIDIA SMI, but it behaves functionally exactly like Ubuntu 2004 VM that you would create. But if you check, see if I can use the, yes. So there is a new confidential compute command for NVIDIA SMI, which you can use to check whether CC is actually enabled on this particular CPU. So if I do G get GPU cap. Yes, so you see CC capable. So in this case, I'm just going to run the proxy application So the proxy application, it generates ephemeral application, which is a Diffie element share to actually do the application level encryption. It uses the TPM to create a TPM endorsement of that key, and then it creates this kind of transparent web server. So now if I go to this, hopefully, yes, you can see that I have this extension installed, I hope. Yes, and it gives, so these are the attestation claims which have been produced by using the Microsoft attestation service and the NVIDIA attestation service on the right side. So this is the information that is available to you to decide whether you trust the remote CVM or not. So right now this is just presenting the information. So in order to kind of get some meaningful security, you need to associate an attestation policy to that website before you use it. So there is kind of this configuration page where you can say these particular fields must be equal to these particular measurements, for instance, for this particular website. And that's kind of how you establish trust in that website. You want to make sure that this is a website that only does RAG and nothing else. So you configure these attestation claims, and then the attestation extension would verify that the policy match. And then it behaves like a regular chatbot. So if I ask about something, then it doesn't really know much about it. But if I upload some document and I ask about it again, then it will be able to use extended knowledge to give a more useful response. Okay, let's go back to the talk. I want to use the remaining time. Yes. I want to use the remaining time to talk a bit about performance. If I can get this to work. Okay. Yes, so performance. So we already covered performance a little bit in the first keynote. And I think the points have already been made, but there are some refined explanation I want to give. So first of all, on the H100s, we have limited bandwidth. So we have loss of 90% of bandwidth. And then we have overheads, which is primarily coming from kernel launch, and the CVM overheads. So if you look at the trends, so this is kind of showing standard application. The overheads is kind of getting smaller with larger models. So we already covered this. I think when you use very optimized deployments, that's my last slide, I think the point is that you get almost zero overheads as long as you are fully compute saturated instead of being IO saturated. And there you can use optimizations, for instance, like CUDA graph, which actually help a lot with the kernel launch overheads, almost completely removing that kind of penalty. So in summary, you can get very, very good performance. Thank you.
Thank you. Thank you. I think we are running out of time. Yeah. Let's have a 5 minutes break and come back. We will have announce our best paper award. Thank you. All right, thank you. We are now moving to the paper presentation section, and before that, we're gonna announce our best paper distinguished paper award for our AISCC. And Jacob, Dennis, are you here? Jacob. Oh, you can go ahead. Yeah, thank you. And the other one, Gelei. Oh, great. All right, thank you. The first one is from Jian from the Indiana University, Bloomington. Thank you.
Let's get started. So hi everyone, my name is Jen. Thanks for coming to my presentation. I'm a PhD student from Indiana University. So today I'm so glad to present my work, security event detection on Twitter with graph-based embeddings. So basically this paper presents a novel method to enhance the security event detection performance on Twitter. So as this study related to the two keywords, security event and Twitter, so I will first answer these two fundamental questions. So what is security event and why is it important? And why do we need to use the Twitter to detect such events? So first of all, what do we mean by security event in our study? So security event in our study refers to any occurrence or incident that have the security implications. So for example, the disclosure of an OpenSSL vulnerability, which is a security event-related vulnerabilities that need to be addressed. Similarly, an event involving the proxy bots is associated with some DDoS or the malware. So another case could be a phishing campaign distributed through the Google Play, which is linked to the phishing tactics. So all of these examples are security events that we aim to detect in our study. So then why is it crucial to detect security events? So for security practitioners and professionals, detecting this event is essential because they serve as a valuable source of threat intelligence. So for example, the OpenSSL vulnerability, it comes with the CVEs listed, which is security experts can use to identify and patch the vulnerabilities. And for the proxy bot-related event as well, it provides a list of IP addresses and hashes that can be utilized for detection purpose. So furthermore, in a campaign event, you might find some phishing URLs. Identifying these can help prevent individuals from falling into the victims. So in summary, security events offer an actionable threat intelligence that can be used for countermeasures and defense strategies. So then why do we need to use Twitter for detection? So Twitter is a vital platform for security communities, serving as a hub for sharing the threat intelligence and the knowledges. So let's take a look at an example. So these tweets are related to the WordPress vulnerability. And each tweet provides a unique insights into the event. So the first tweet details the IP addresses involved in the attack and offering a specific data points for the analysis. And on the other hand, the other tweets list the CVEs associated with the vulnerability and the method used for these attacks. So the diversity in the contents highlight the tweets as a valuable source for security professionals, helping them to gather the wide range of information for emerging events. So more importantly, Twitter is also known as the first platform to report the latest security events. So in these two screenshots, the top part shows an article from the news outlet, the Hacker News, and the bottom part is from the Twitter. So if you pay attention to the dates, you will notice that the information on Twitter was posted 2 days before it was appeared on the Hacker News. Also, these advantages have also proven by the recent studies, which shows that the security events tend to have report in the Twitters first than the other news mediums. So then how to identify the security events? So the common practice is using the text embedding to embed the tweets and using the clustering algorithms to clusters. However, there are some force similarity issues in the existing text embedding method. So when we come to utilize the security and the Twitter context. So here's an example. So in this picture, there are two events represented by the purple dots and the pink dots. And these tweets are embedded word track, which are commonly used in the existing security event detection literature. However, the distance between the T1 and T2, which belong to a different event, are actually smaller than the distance between the T1 and T'(E1, which belong to the same event. So considering the clusterings are based on the distance, it will suggest some false clusters, which in turn will degrade the performance of the security event detection. So which means that we need a specialized tweet embedding method for security event detection. So in our approach, we introduced a novel method for tweet embedding called the tweeters. So this method is based on the intuition that different events tend to have different security attributes, such as threat actors, victims, and organizations. So we believe that identifying these attributes is crucial for distinguishing different security events. And also to categorize the security attributes effectively, we rely on the definitions on the STIX2 objects. So STIX2 is widely used, widely recognized as the standard framework for the cyber threat intelligence. So it offers a comprehensive set of attributes that are essential for detailed and structured analysis of the threat intelligence. So we try to use this list, and to also effectively leverage this information, I mean the security attributes for event detection, it's important to identify which tweets share the common security attributes. And to effectively organize and present this information, we employ graph structures. So we then utilize the graph neural network to generate the embeddings, which has been already widely used for capturing the complex structures of the graph. So let me briefly work through our overall workflow. So first of all, we start from the feature engineering, in which we try to encode the two essential information for security event detection, which are text and the temporal information. And on the other hand, as I mentioned in the previous slide, we extract 6 entities from the tweets. Here we use the large language models with some prompt engineering method to extract the entities. And these extract entities will be serve as the input to construct the graph. And together with initial features and the graph, both of them will serve as the input of the GATV2, which is one variation of the graph neural network, and generate the tweet embeddings for clusterings. So this is the overall workflow of our method. And let's move on to talk about our experiment. So to evaluate the clustering effectiveness of different embeddings, we create our own data sets. We begin by identifying significant events from the 3 different sources, like the Hacker News, Flipping Computer, and Hangmegaden. So we then collect the tweets related to these events using the Twitter Enterprise API and match the tweets with the corresponding events. And we divided this data set into three sets, training, validation, and testing. Each sets are in distinct time frames. And this separation allows us to simulate the realistic scenarios where the model trained on the past will also work well on the future data. And also, and this is the experiment results. We use the 3 key clustering evaluation metrics where the higher score represents the better performance. So our approach is compared with the traditional word embedding based method like TF-IDF word fact. And we also compare our method with the pre-trained language models. Here we also use the secure BERT and the BERT tweet, which are BERT-based models that are further trained on the security and the Twitter corpus, which is the focus of our study. So additionally, we also evaluate our graph-based method with graph-based method, so which have been seen some applications in the social event detections. So we also compare our method with the graph-based method, and the experiment results suggest that our method outperforms our existing method. This is because our method design, in which, as I mentioned earlier, is tailored specifically for security event detections. So this is the working in progress study. So we have following 2 things as future work. So first of all, we plan to develop an end-to-end framework. This will enable our design method to work well in the real-world settings. Secondly, we aim to demonstrate some use cases for our framework. So we will try to find some high-profile security users, and we will also leverage our framework to do some security trend analysis. So this is our future work, and this is for my presentation. So if you have any question, please feel free to ask.
Thank you, Jen. Any questions? Questions? Okay.
Actually, at some point, you added time information to the graph embedding, right?
Yes, right.
What is the reason for adding this time information?
Oh, yes. This is basically based on the intuition that the same events, a tweet belong to the same event, tend to exist in the same time frame. So that's the intuition why we use the temporal information.
Okay, it means it's similarity of the instance. Or do you mean similar events are coming in the similar times? Or?
I mean, the tweets belong to the same events, tend to appear in the same time frame.
Different places.
Yeah, yes, right, yeah.
All right, thank you. Okay.
Could you please go back to the dataset generation and how you constructed the dataset?
Sorry?
The dataset of how you constructed the dataset and what the dataset actually is. Could you please go back?
Okay.
And
You mean
just
here? Yep.
yes. So, what are you doing with all of those events from Hacker News, Bleeping Computer?
So basically, these experiments, you try to measure the clustering effectiveness. So you will list some events associated with some tweets. So we want to see how good the clustering is when we apply different embeddings. So we try to compare our embedding method with some existing techniques to see how better can distinguish different security events. So security tweets, yeah.
So you are looking at the tweets from those sources?
Actually, these sources are just find some notable security events, and we try to get some tweets related to this event and match the tweets, and we try to get the clusters that we want to find, and we will compare the embeddings based on that, yeah.
All right. Thank you, Jian. Let's moving forward. Next one is Tianhang. I think this one, Tianhang, is in the Zoom. So let me. Tianhang, are you here? Sorry. Oh. Does the projector can present the Zoom? Or we can, if there's still the technical issue, we can move to the next one. Lincoln, let's move to the next one, waiting for the technical issue solved. Lincoln is here? Yeah, please. Yes, please. Oh. Okay, so it's not working on it. Okay, all right.
Okay, good morning, everyone. I'm Lincoln Du from the University, and today I want to present our new work about the artworks copyright auditing for text-to-image model. And this is a joint work from the University, Stanford University, and the CISPA. And many thanks to my co-authors in the following. And today, the text-to-image model has gained a significant traction in text-generated image fields produce high quality of the synthetic contents. And they usually contain two processes. The first process, the forward process, gradually adds the noise to the image over a series of steps until then becomes a random noise. And the reverse process reconstructing the image from the random noise. And the text is one of the conditions in to guide the model to generate the desired images. With the development of the text-to-image model, the user without the painting knowledge can use simple prompts to generate the high-quality images. And here is the model trained with original artworks, and they can mimic the artworks. And the other one is the fine-tuning with the original artworks, and you can see the quality is very good. So because the huge overhead to train the text-to-image model from the scratch, the adversary usually use the fine-tuning technology to train the text-to-image model. Use a small set of artworks, and if we want to conduct the copyright auditing, we want to check whether the suspicious text-to-image model used artworks by a specific artist during the fine-tuning process, like the following auditor. So here we want to price some assumption about the auditor. The first one is the auditor's knowledge and capacities. First, we assume the auditor has the full access to the artist's artworks. That's the, for example, some images to be auditing. And the auditor only have a low-end customer GPU to extract the style presentation or to process the artworks. And finally is the black box access to the suspicious text-to-image model. And the auditor goal is to check whether the suspicious model use artist artworks during its fine-tuning process. Yeah. Here we summarize the existing solutions in this field. And the first one is the adversary perturbation-based measures. And the second one is the watermarking-based measures. And the adversary perturbation-based measures introduce some perturbation into the artworks and alter the latent features in the diffusion process. And they making the model unable to generate desired images. And the watermark-based methods inject well-designed watermarks into the artworks or other samples before sharing them, so they can trace the training process of the text-to-image model. But they face three main limitations. The first one is they need to manipulate the original images. And second one, they rely on the fidelity of the perturbation or the watermarks. And a final one, they can't handle the image that have already been published. Sorry. Here we provide the intuition of our proposal from the below the top, and we here we can see the artworks of artist A, and we use the fine-tuning to mimic the artist's work of artist A, and and the right is the artist's work of artist B, and we use the style extractor to collect multi-granularity style representation of the artworks, and the top is the style representation of artist A and artist B, and then we use the discriminator to predict whether the generate the style presentations to measure their similarity and to output the decision whether they have copyright issues. Here we go to the details of our proposal, and the style auditor has 3 steps. The first step is auxiliary dataset collection, and the step 2 is discriminator construction, And step 3 is the auditing process. So in the first step, here the auxiliary datasets contains artworks from 2 sources. The first one is the public artworks and generated artworks by the suspicious model. Here we assume there are some what famous image in the pre-training datasets of the text image model, like the artworks from Van Gogh or Picasso. And we use these artworks and generate some captioning of these artworks and use the prompt to stimulate the text image model to generate the mimic artworks. Okay. What happened? Yeah. And then we collect the public artworks and generate. Sorry. Okay. So we finished the auxiliary dataset connection. And in the second step, we built the discriminator, and the discriminator was trained with target artist artwork and the public artwork and the generated artwork. And the style discriminator, we used the convolutional neural network, that's the CNN models, as the basic framework. And the discriminator model used the style instructor, the style representations, to predict whether there exists the copyright issues. And in the step 3 is the auditing process, and it's similar to the step 2. But here is the suspicious models. So we extract the multi-granularity style representations of the mimic artworks and query the discriminator trained in step 2 to obtain the auditing decisions. And we come to the evaluation. So we adopt the Stable Diffusion version 2.1 as the suspicious model, and we construct a dataset from 30 artists, which are not in the pre-trained datasets of the Stable Diffusion. Here are the details of the information of the datasets. First, we show the performance of the text model. That's the imitation ability of the suspicious model. The first part is the original artworks, and in the middle is mimic artworks without fine-tuned with original artworks. So they are maybe different from each other. And the last one is the mimic artworks when fine-tuned with the original artworks. So it can see there share some similar features among them. But we also notice some infringements cannot simply be judged by the naked eye. And here is some auditing performance we can conduct. And we can see the accuracy is 19%, and we have a low false positive rate. Finally, we conclude our contribution of Style Auditor. And Style Auditor provides a new perspective for dataset copyright auditing for text-to-image generative model. And the Style Auditor is the efficient solution that only requires the consumer-grade GPU computing power. And we demonstrate the effectiveness of our proposal on Stable Diffusion. But there are also some limitations need to solve. The Style Auditor may insufficient response if the suspicious model performs some adversarial strategy on the generated content, as known as the adaptive attacker. And I want to show my gratitude to my research group and my director, and we are hiring. Now, please refer to our website for more information. And that's all. Thank you all.
All right, thank you.
Yeah.
We are running kind of late, so maybe just one question. Any question?
Have you considered other domains this might apply to, like audio?
Yeah, thanks for your question. In this paper, we only consider the image domain. Maybe you want to ask about the synthetic audio. No, we only consider the text-to-image model. Maybe it's a promising future direction. Yeah, thanks for your question.
Thank you, thank you. I think our technical issue has been already solved. So let's move on to Tianhang, which is he will show the he will do the presentation through the Zoom. All right, Tianhang, are you ready? We cannot hear you. Can you check whether you muted yourself? If that case, should we move to the next one and maybe check back to later? Okay, Jacob, can you do the next one? Yeah, thank you. All right, here. Yeah. All right, great. Yeah, good.
All right. Hello, everyone. My name is Dennis Jacob, and I'm going to be presenting on multi-label patch cleanser, which is the first certifiably robust defense against a patch attack in the multi-label classification domain. So first, a bit of background. So what is an adversarial patch? Adversarial patch is a specific type of adversarial attack where an adversary is allowed to basically adjust pixels in a constrained local region. One reason why these types of attacks are very interesting is that they're actually physically realizable in a variety of different applications. So on the left, we have an example of an adversarial attack in an image segmentation model. And on the right, we have an example of an adversarial attack on a single label classifier. And in both cases, you can like print out a sticker or make like a billboard and actually fool classifiers or models doing so. So how do we defend against these types of attacks? One idea is to do what we call an empirical defense, and this is where you use empirical observations to create a defense against patch attacks or other attacks. But one issue with these types of attacks is they're vulnerable to what we call adaptive attacks, where basically you can use the empirical observations that were designed for the defense to circumvent them and basically cause poor performance on the model. So alternative method is to use certifiable defenses to provide provable guarantees on robustness. Finally, also briefly touch on multi-label classification. So this is basically similar to single label classification, but the main difference is that you can have multiple objects in an image instead of just one. So an example here is we have a picture here with a dog, a bicycle, and some people in the background. So if you feed this into a multi-label classifier, you'll have, okay, there's a dog, there's no cat in this image, so we'll have the following metrics. The true positives will be person, dog, and bicycle. True negatives will basically be every other class, and we won't have any false positives or false negatives. Now, how could we attack this model? Well, an attack is going to aim to induce false negatives and false positives. So here we have an example of a patch on our image. The patch is now going to say, oh, there's no dog anymore in the picture. Obviously, there's no cat. So we're going to have true positives of person and bicycle, but now we're going to have a new false negative of a dog. So this is an example of a successful attack. So once again, what is our goal? Our goal is to design a certifiable defense for patch attacks in the multi-label classification domain. This currently does not exist, so we are the first to kind of address this problem. And to this end, we propose multi-label patch cleanser. This is essentially an extension of an existing state-of-the-art defense for single label classification called patch cleanser. So I'll kind of briefly touch on what patch cleanser is. Basically, the way that patch cleanser works is that it curates a set of masks which will cover the patch regardless of location. And the main security invariant that makes patch cleanser successful is that a masked clean image is always going to be predicted correctly. This is also known as two-mask correctness. So I'm going to briefly go over an example run of the inference algorithm in patch cleanser. So the way it works is that there are 2 rounds of masking. And the first round of masking is where we aim to cover the patch with a mask. So here we have an example of a dog with a patch in the top left corner. So during the first round, we're going to basically have a mask and just slide it across the image. And we're going to query the model output for several times in a row with different mask locations. Notice here that the only case where we have a correct prediction is when the mask covers the patch in the top left corner. Every other case, we have an incorrect prediction. And based on this observation, we can define a notion of disagreeers, which are basically outputs which are not the majority prediction. And the idea is that we're going to perform a second round of masking in order to extract some useful information on these disagreeers. So specifically, we take one of the disagreeers where we had the mask covering the patch, and we're going to run a second round of masking where we keep the first round mask fixed, but we're going to now slide a second round mask over all the images. And note in this case, the invariant from earlier, that the security parameters that basically any time when we have a masked clean image, we're always going to be predicting it correctly. So in this case, because we already covered the patch with one mask, every single case with a second round mask is going to return the correct output, so we have certifiably recovered the correct output. So in general, basically with patch cleanser, the 2 robustness criteria are 1, you want to have a mask set in which you can cover any patch of a specified size. This is called R covering. It's discussed a bit more in the patch cleanser paper, so you can read that if you would wish. And the second, of course, is the invariant, which is two-mask correctness, which is basically if you have a masked image and you cover the patch, you're going to return the correct label. So based on these robustness parameters, you can actually provably show that patch cleanser will always return the correct label. For timing's sake, I won't really go over the proof, but that's kind of the basic idea for why patch cleanser is provably robust. Okay. So now how does this relate to the multi-label classification domain? Multi-label patch cleanser, the main intuition here is that we can apply the double masking algorithm from patch cleanser to each class separately. So once again, we have an image, we feed it into our multi-label classifier, and we can basically query every single individual class one by one and run the double masking algorithm on it. The reason that this works is because each individual class in the multi-label setting is essentially independent of each other. So you can consider each of these to be a separate set of series of binary classification problems where you can apply patch cleanser to each one individually. Robustness can be defined pretty similarly in the multi-label case. So once again, generating the mask that can cover the patch, this R covering property is the exact same as the original patch cleanser paper. The main difference with regards to robustness is that we're going to define robustness at the class level instead of like an overall level, and this is because, again, in a multi-label setting, you're going to have more than one class that can be in an image. So based on this, essentially, if a class is going to, meet the second, class 2 mask correctness parameter, we are going to call it certified. And if a class is present in the image, it'll be a certified true positive or true negative. If we don't pass the certification protocol, this step 2, basically we'll consider it to be the worst case, or it will be a false positive or false negative. And because we're lower bounding true positives and true negatives, we can basically define notions of precision and recall and lower bound these for a particular image. And extending this to the rest of the data set isn't too difficult. So some results based on this. We have 3 settings, essentially. The first is undefended clean, and this is basically where you have the multi-label classifier by itself with no defense, you can see that precision recall metrics are relatively high. The second setting here, defended clean, is when we apply our multi-label patch cleanser algorithm to a undefended model. And you can see that the performance is pretty close, except that there's a slight drop in recall. And finally, the robust, certified robust is where we apply the concepts in the previous slide with the 2 R covering and 2 mask correctness, and we achieve non-trivial robustness in this case. We also try varying across a different set of thresholds, and basically the idea here is that we want to see trade-offs in precision and recall as we vary the threshold over time. And here, once again, we can see that defended clean performance tracks similarly to undefended clean, and then certified robust performance doesn't track as well, but it is still non-trivial performance across a variety of thresholds. So the final thing I'll talk about is histogram-based certification. This is a novel concept that we developed. And the idea is that we want to establish some tighter bounds on robustness. The intuition is that some of the double masks which cause failure across different classes might be different. So we return to this dog image here. So during certification, when we're trying a bunch of different double masks, and we want to see if we can certifiably prove the accuracy of a given class, we can see in this case with the right image that the 2 masks occlude the dog, so it causes failure in certification for the dog class, but it doesn't impact the bicycle on the left or the people in the background. So this is an example of double masks which cause certification failure in one class but not in the other classes. So another observation is that an adversarial patch in our model can only be placed at one location. So based on this, we're going to define a concept called certification histogram for every single class that failed our 2 mask correctness property from earlier. And essentially what this is for a given failed class, we define like a vector or a 2D matrix, where essentially a cell is marked as the corresponding mask to the cell is involved in certification failure. So let's look at some examples. So we have one of the images from before, and we're going to inspect the highlighted mask there, which corresponds to basically right here, this cell. And the way we want to check if we want to mark this cell or not is we run a bunch of double masks with the red mask, and then we also run over every possible second mask that could be present. It turns out in this case that whenever you do this for this specific example, it does not lead to certification failure for the dog class, so we do not mark it. Of course, in this case, we do know it leads to certification failure. So if we look at this highlighted mask here, we know that it's going to lead to failure for the dog class, so we mark it. But in addition, because the other paired mask also contributed to failure, we have a symmetry property here, so we had to mark both classes. So this ends up being the final histogram for the dog class in this example. And the final thing we can do is that for each of the individual classes that failed certification, we can add these histograms together. So for dog, for bicycle, for person, and we'll get this total histogram. Now, the total histogram is unique because each individual number in the cell basically represents how many individual histograms failed before you added them up. So in the worst case, for inference, is going to occur when a patch is basically placed at a cell with the largest value. So essentially, if a patch is placed in this location with the largest value, it's going to cause a maximum number of classes to not meet the 2 mask correctness property. Notice, however, that classes which are not included in the cell will be predicted correctly despite failing certification overall. And the reason for this is because when the patch is placed at the worst case cell during inference, we know by definition of the certification histogram that any double mask involving that cell would have been predicted correctly. So therefore, we have this kind of residual robustness property where the class that was not accounted for in the histogram will actually be predicted correctly overall during inference, even though our traditional notion of certifiability was not met. So based off of this, we have some residual robustness, which improves upon our bounds. So the old certification method is here. We can see the precision recall metrics. And we have 3 kind of cases to consider. So we have a worst case, FN attack, FP attack. FN attack is basically where we only consider the false negative histograms. FP is where we consider only the false positive histograms. And worst case is where we consider both in conjunction. So in conclusion, we propose multi-label patch cleanser as the first certifiably robust defense against patch attacks in the multi-labels classification domain. And we additionally designed a novel histogram-based method for capturing residual robustness. So next steps include trying to design a better inference algorithm based on this histogram observation. Another interesting step is that vision transformers have been shown to be more robust to cutout and masking properties than ResNet backbone, so we're going to investigate trying to use that instead. There are other training tricks we can use to improve performance, such as EMA, cutout training, et cetera. And finally, of course, more data sets to verify our performance across more benchmarks. That's my presentation, yeah.
Thank you.
Yeah.
All right, thank you, Jacob. We have one question. Is there anyone want to have a question here?
Hey, what is the effect of the size of the patches and the masks on the detection?
Yeah, so the mask, yeah, sorry.
Yeah, both adversarial and your detection purposes.
Yeah, so basically the mask generation process that we use in this work is taken from the original patch cleanser work. And the way it works is that you need to provide like a security parameter. So you had to kind of estimate how big you think the patch is going to be. So some common estimates are like, say, a 2% patch where the patch covers like 2% of the image, or maybe 4%. But given if you have like a certain size estimate on what you know the patch is probably going to be, you can basically, that will inform the mask generation process, which will guarantee the provability of your system. But you can kind of intuitively expect when you have larger patches, performance does get worse because the larger your patch, the larger your masks need to be, and that leads to more possibility of like covering up essential items in your classifier. Yeah.
All right, thank you, Jacob. And now we are moving to the previous one, Lincoln. Can you connect to the Zoom right now? Oh no， 林康讲完，抱歉。All right. Oh, sorry. A lot of tech issues today. So it's still, is there any other ways? We have to move to another one again. So, Angelo, are you ready to present? Angelo, from IBM Research. Okay, great. Thank you. Oh, this one. Type C. Oh. All right.
Okay, yeah, thanks everybody. My name's Chris, actually, not Angelo. These are all my teammates who worked on this, including Angelo, Claudio, Daniele, Darren, Hubertus, who's here, James, Marcio, Mengmei, Nitish, and Tobin. So thanks to all of them. So I'm presenting our talk titled Aligning Confidential Computing with Cloud-Native ML Platforms. So this stemmed from this observation that, yes, confidential computing projects are powering forward, and these ML cloud workloads are obvious candidates for this technology. And we can even run ML workloads today on these confidential computing environments. But like there's a whole ecosystem of ML frameworks that has come up recently, and they're improving productivity, but they're not necessarily congruent with the confidential computing technologies. So content of this talk, I'm going to scope this a little bit more because we only have so much time. I'm going to present several challenges that we foresee here, and then I'll try to put this together to show how we think this will look. So in terms of scope, confidential computing it's really broad, right? You could be talking about VMs, you could be talking about containers. If it's containers, what kind of orchestration are you using? What kind of hardware are we running on and all of this? And ML platforms is sort of just a word of the day maybe. In general, I'm really referring to like ML ops tools here. So these are like AWS SageMaker or Google Vertex AI. And if you start narrowing down, you see that there's a lot of features that don't even have overlap potentially with confidential computing. So like some of them just help you manage your models, for instance. But if you look at ML pipelines specifically, it seems like a really good candidate for confidential computing support. Okay, so for the purposes of this talk, I'm just going to look at one project, which I actually work on. It's called Confidential Containers, or COCO. And I'm going to look at ML pipelines, and I'll use Azure to give a few examples. So if you've never heard of these, I'll give you a quick run-through crash course. You don't have to understand everything on this slide, but this is the threat model for COCO. And I want to draw your attention to two things. One, this is the Kubernetes control plane, and it's not running inside of that green box. It's running outside of the trusted execution environment. And the second thing is the Kubernetes pod, the workload itself, is inside that trusted execution environment. So we've heard a little bit today about this, but basically the cloud service provider, among other things, is not trusted here. And this is drawn from Azure's website for their tutorials on ML pipelines. And I want to show you just that this is how you can envision your computation running in their cloud. This is a directed acyclic graph. It's got computation nodes, so you can prepare your data, you can train your model, and you can score your image. Okay, so those are the two technologies, and the question becomes, in addition to that too, you also have data dependencies, right? These are your edges. So the question becomes, how do we unify these two technologies? So one challenge to bring out, this is really just bookkeeping, but it has to be said, right? COCO it has some assumptions about hardware, firmware, kernel support. And any ML pipeline in the near future needs to be concerned with this. So you can't just launch your ML pipelines on any hardware and so on. You're going to have to take these into account. Specifically, and we heard some of this today, GPUs is a big one. So this is still novel support. So like you'd have to take this into account with an ML pipeline today. The second thing is that COCO, and there are other platforms out there, but COCO has its own environment assumptions. Okay, so one of those is it assumes you have some custom operator in Kubernetes. A second is that the control plane itself is not virtualized. It could be, and when it is, COCO has some ways to handle this. But what that means is that if you're going to run an ML pipeline and you're not taking this environmental assumptions into account, you're going to have problems, and you're going to have to adopt certain features of the confidential computing platforms you're using. The third one, this is kind of minor, but kind of not, right? Like there's no ML pipeline today that I'm aware of that actually exposes a way for users to actually indicate they want a confidential environment. So that's just a feature that has to be added. In COCO, we do it with YAML files. ML pipelines, they have ways of configuring things, but at the end of the day, you might want to add something like in the YAML for your ML pipeline. Now, challenge 4 is where things start to get a little bit tricky. So you have features in your ML pipelines that they don't take confidentiality as a first-class concern. So I'll give you one example that I am aware of. AWS SageMaker, it allows you to cache your pipeline steps. So you run your you do some training, for instance, and then you don't want to do certain things again, you can cache that. But if you don't trust your cloud provider, should you be caching? Is it okay to cache? Where is it cached? These sorts of things. And then challenge number 5, this is really the bread and butter of it all, but I saved it for last, which is that ML pipelines, they're not designed to work with protected nodes and edges in their DAGs. That's really the thrust of everything here. That the DAGs are just completely unprotected. So what do you need to do? If you have support for specifying mounts inside your ML pipeline code, these need to be encrypted mounts when they're actually actualized at runtime. All computations they need to be encrypted before they're uploaded. So I've never worked directly inside of these ML pipelines, but as I understand it, they're going to have to, you're going to push your code up, and then it's going to pull them down onto one of these Azure infrastructure nodes, right? And that has to be done in an encrypted manner. And then the trusted client-side library support needs to be somewhat open to the user. So for instance, if you're using Azure libraries, you have to either have some sort of open source library support there, so that because they're also your cloud provider in this case. So you can't just necessarily assume that they're going to take your Python script and use it without leaking something. And then lastly, this is a subtle point with Cocoa, but some other container technology. So we have these relying parties, as they're called. These do attestation, and they release secrets. And this relying party is going to need to be deployed in any ML pipeline environment. Okay, so I'm going to put this together visually to kind of close this out. So this was the DAG I showed earlier for an ML pipeline. And let's just take one of these nodes, so scoring. Still drawn from Azure's site, so this is the code for scoring. There's a little bit more to it than this, but at the end of the day, it's a Python script, right? And you can put it in score.py, and that's your computation. So today, if you're going to launch score.py on Azure infrastructure, you launch your pipeline, and it manifests in this node, right? And what has to happen in the near future, if you're going to use these in confidential computing, is it needs to be running inside of a T. The same applies for all the nodes, and the edges between them, the data needs to be running in, or needs to be stored in some sort of encrypted storage or passed in some encrypted channel. GPUs, which we've touched on today, if you're going to use those, you have to extend your T at runtime to include that GPU. And I talked about relying parties at the end. So these relying parties, in this diagram for this Cocoa threat model, these relying parties need to be deployed somehow in the system where you're running your ML pipeline. Okay, so to cap it off, confidential computing projects, they do support ML workloads today, but users are developing and deploying ML solutions with frameworks that don't have a notion of it. And at its broadest, at that broad level, there's a lot of open problems. And specifically here, I'm just talking about what we think a Cocoa enlightened ML pipeline could look like. There's challenges, but we do think it's feasible. All right, so thank you.
All right, thank you, Angelo. Is there any question? We only can get one question in here. If there's no question, let's move to the online presentation again. Thank you.
Can you speak?
Mic is muted. Other one's muted.
It says that the host is disabled. Sharing.
From University of Minnesota. 没法插那个，只能插这个。
Hello everyone. I'm here today to present our work exploring the influence of prompts in large language models for security-related tasks. The emergence of large language models such as ChatGPT has marked a significant advancement in the field of AI. Their broad and powerful capabilities interest researchers. Prompting exploration of various applications such as Stable Diffusion, DALI, and GitHub, and etc. Specifically, large language models have been shown powerful impacts in security-related problems, including vulnerability confirmation, patch commit, and etc. In addition to that, recent work found that large language models can help improve the SOC security, power the binary intent analysis, help improve fuzzing performance, and so on. A recent study also indicated that modifying prompts can significantly impact the effectiveness of large language model in completing various tasks. So the traditional prompt engineering works bring out several types of prompts to improve the performance of the large language models, such as modifying the definition of the ChatGPT system, adding emotion to GPT, giving few examples to GPT, zero shot, chain of thought, and etc. So in our work, we are trying to answer the question, can these prompt techniques be adapted for security-related topics? So the aim of our work is to answer the following questions. We try to investigate the influence of different prompt structure. We are trying to investigate the influence of different prompt structure, different prompt content, and a combination of different prompt content. At first, we will introduce the dataset we are using. So first, the security patch detection. The security patch detection is to identify if a program patch is security related. The second one is vulnerability function detection. Vulnerable function detection is focusing on identifying functions that include vulnerabilities. And the last one is stable patch classification. The SPC determines if a patch should be integrated into a stable version of Linux. So at first, we will introduce two terminologies, prompt structure and prompt content. Prompt structure refers to the overarching framework or format of the prompt, which dictates the mode of interaction with the large language model. We select zero shot, one shot, and few shot prompt in our work. In details, for example, we split one shot into one shot T and one shot F, which means we provide one positive example and one negative example in prompt respectively. Similarly, the TT means two positive examples, and the FF means two negative examples. For TF and FT, we select the same positive and negative example in prompt. However, we put them in different sequence, which is to investigate the influence of the sequencing of the prompt. The prompt content represents the sentences used in the prompt. For example, if the objective is to have ChatGPT generate an image of dogs, so we will provide the prompt content. please create an image of dogs to the ChatGPT or other large language models. We categorize prompt content into 3 categories. The first one is role related, which includes changing the role definition in default system role setting and providing role definition in prompt input. The second one is GPT-generated prompt, which is generated from ChatGPT-4 by giving ChatGPT the task description and let the ChatGPT to generate the prompt. The third one is emotion-related prompt, such as encouraging or threatening GPT or offering ChatGPT a reward or punish. For the evaluation setup, we select the GPT 3.5 Turbo as our model, and we use accuracy, recall, precision, FS score as the matrix for the evaluation. The table shows the result. The influence result of different prompt and structure, and the prompt content is shown all this in the table. Following on different matrix, we can see that different prompt structure or different prompt content performs better than others in different security tasks. Also, we can see that there's no perfect prompt suitable for all the security tasks, which means the performance of the prompt changing with different security-related tasks. We will show the conclusion of the AIM-1 and the AIM-2 in our work. First, from the result, we can see that there's no universal best prompt content and prompt structure. Rather, there's only the most suitable content or structure for a given task. Second, our results do indicate that altering and testing different prompts can significantly change the large language model outputs. For instance, in our 3 experimental tests, the lowest recorded accuracies were 41%, 22%, and 40%, with the highest accuracy reaching 61%, 54%, and 54%. This represents a substantial variance of about 13% to 30%. Furthermore, in scenarios where the objective is to specifically reduce false positives or false negatives, tailoring the prompt for the large language model can effectively achieve these target goals. Also, we compare our result with zero-shot COG with zero-shot channel salt. We add data things step by step to the basic prompt content. And the zero-shot COT does not excel in any task. However, we cannot directly get a conclusion that zero-shot COT cannot perform very well in security-related tasks because we need to do more evaluation to get the final conclusion. To achieve the aim of our research, the third aim of our research, investigating the performance of combination of prompt contents. We did a comprehensive combination of prompt content. This example shows the combination of role definition and emotional encourage. We can see that you are an AI expert in patch analysis. It's kind of like a role definition in the prompt. And for the last sentence, remember you are the best AI patch analysis. It's kind of like to encourage the ChatGPT. When combining different prompt content, there is only a small likelihood, about 9%, of enhancing the large language model's performance beyond what is achieved using 2 separate prompt content. In the majority of scenarios, about 50%, the results of combining the prompts fall within the range of those obtained from the original single prompt content. For the remaining cases, about 41%. The result from combining prompts are always worse than using each of the prompt contents separately. For certain tasks like vulnerable function detection, the strategy of combining different prompt contents tend to be ineffective, always yielding results that are worse than those obtained by using the prompt content separately. From the result, we can conclude a conclusion of AIM-3. In most cases, combination is not a good idea to improve the performance of the large language models. So here's our conclusion here. First, there is no perfect prompt suitable for every security-related task. Second, changing prompts can significantly affect the performance. The third is that a combination of prompt contents is not a good choice. So that's all. Thanks.
All right, thank you. Is there any question? Oh, okay.
Actually, you said that you did something for emotion,
Yeah.
different. So you are giving one question or one prompt about specific emotion.
Yeah.
How you can deduce that it is related to emotion, but it's just different question or prompt? How you can relate that it is about your punishment emotion? For example, did you check different prompts which may mean punishment, but different things at times you can deduce something that, yeah, punishment is better than encouragement or something like that. Did you get me, my question?
Yeah.
Yeah.
I understand your question. We borrowed this idea from a previous work. They said the emotion may affect the performance of a large language model. So they provided their prompt about the punishment or encouragement. So we kind of like modify that prompt for the security-related task. For example, just say you are the best AI. You are the best AI patch analysis. But for the original prompt, it's you are the best. You are the best person. Something like that. Did that answer your question?
Yeah, for example, if you ask, you are exactly very good in this case, or different prompts, it gives similar result, and we may relate it with the emotion. But if there's just one question and seeing differences, I'm not sure if we can say that it's related to the emotion.
Okay, I got the point. We can do more evaluation about this part. Yeah. Thank you.
Oh, thank you. Next one, Zhen. Thank you.
Okay, so good morning, everyone. I'm Zhen from Wisconsin, Milwaukee. This work is done by my student, Isra. She is a full-time product security engineer at Rockwell Automation. So due to some work confliction, so she couldn't be on site. I come to present this work. This is our initial work on using large language model to facilitate the threat modeling in operation. Let me give some background on threat modeling. So threat modeling is kind of like a critical process in the product design. So when we design the product, we involve the product security engineering into the product teams and try to identify how attacker could potentially attack our product. So in that way, security engineer will try to identify the potential risk or understanding the security, understanding the threat landscapes for this product. In that way, when we design the product, we could better apply some protective mechanism in advance. So that's from the beginning of the product design to its deployment. So that's how it usually works in operation for the threat modeling. And there are 4 big types of questions we try to answer in threat modeling. One is, what are we working on? So this question is to understand the product design. The second question, what can go wrong, is more related to the security side. We want to try to understand what's the potential threat we might face for this specific product. Another question is, what are we going to do about it? It's more about defense, how we better design to apply some defense mechanism during the product design to better protect our product. And the last question, did we do a good enough job? So that's more about reflection. So when the product, when we have the prototypes, we will check, is this secure enough? So that's the 4 main questions we usually cover in the process of threat modeling. Now we have some background about threat modeling. Now let's move to our work. So in our work, we just focus on a specific process. So threat modeling covers a lot of questions, and for our work, we target the first 2 questions, and we mainly focus on the kind of like the communication between the product security engineer with the product architecture. So in that way, we try to understand what's the design of the product and how to better protect it. We see there is a flow chart to show how threat modeling are integrated into the product design. And it also involves the communication between multiple roles. So here, the product engineer have some challenges in this process. In our work, we target 2 challenges. The first one is the requirement on the skill of the product security engineers. Since we know the threat modeling requires the engineer to try to translate the very abstract theoretical security concept into a more applied or practical defense on the product design. So it requires the security engineer to fully understand both the product and also have a strong background on security, and also use that security background to into the product design process to guide the product architecture to refine their design. So it has higher requirement on the security engineer itself. And also, we noticed that in this process, they keep expanding landscaping. This threat landscaping also bring more challenging to the security engineers. For example, based on the NVIDIA record, there are over 27,000 vulnerability. New vulnerability has been added into the NVIDIA. So to keep updated with this newly increased vulnerability also bring more challenging for the security engineer. And our work will try to address this 2 challenging. So in that way, our design is more focused on how to reduce the human effort in the process of threat modeling by utilizing the large language models. So this is our design, the overview of our design. So in this process, we identify 3 main processes. So the first is try to extract the key characteristics from the input and also build up the knowledge base based on this input. And we use the large language model to answer the question, the threat modeling related questions, to suppose the security engineer better work on their tasks. There are 2 main types of questions we cover. So we know there are 4 main types of questions of threat modeling. And for our work, since this is a very initial work, the preliminary study for us, we focus on the first 2 questions. The first one is, what are we working on? So that part, we try to understand the design, the system design of this product. And the second task is what can go wrong. So let's try to understand the associated vulnerability or risk associated with this product. So in this part, our input data contains two types of data. One is a design document for the product, and another part is a vulnerability from NVIDIA. So we we make the vulnerability from NVIDIA up to date for every analyze. Here are more insight about the question we will ask in each task. So we will cover the topics for the system description on system environment and data for the task 2 to understand the product. And for the second task, we will focus on the security side to understand the key management, the identification, access control, or network configurations. In the evaluation, so in our system design, we use the Llama 2 and also RAG to develop the large language models. And for the evaluation part, we set the threat modeling question queries based on the different type of questions. That question has been validated by the product security engineer. We get response, we evaluate the response from the model, and we do the human evaluation. Since in this task, we want to identify, does this response really make sense to the engineer? So we think human evaluation is more intuitive way to do that evaluate. And do the evaluation based on the satisfaction rate for the response. For example, here, the positive one means we think this response is satisfied by the engineer. And because that response is more concise and more precise with the valuable information provided to the engineer for the next step, decision making. And the response we think is not satisfied, that means such a response sometimes is too general. And we know language model just talk for talking. So we want to figure out how valuable information could get from that response. And also we do some comparison by using the base language model and also compare it to the RAG-based language model. And we find that the RAG-based language model will provide more concise and more precise response. Also, it's interesting to see that the RAG-based language model will kind of like show the awareness of honest. So if we give some information and they think the information is not enough to suppose their response, it will just say based on the provided content, I couldn't answer this question. So that's our observation, interesting part 1. Okay, so for the conclusion, as I say, this is the initial study. We know we have many room to explore more, either the evaluation case or the different types of question for threat modeling. But we hope this part could support our next study on explore more how to utilize large language model to reduce the human effort in the security activity in operation. So thank you.
Thank you. All right, thank you, Jin. Is there any question? Anyone has a question? All right. If there's no question, let's have a 5-minute script.
I'm going to start. Good morning, everyone. My name is Chen Zhuo. I'm from Wuhan University. I am honored to present our paper, Research on the Reliability and Fairness of Opinion Retrieval in Public Topics. Today, we obtain information from many sources, including search engines, recommendation systems, and social media. They usually adopt deep neural network to select and filter information. On one hand, existing research has identified reliability defect in information retrieval models. As shown in the bottom left picture, adding specific perturbations document candidate can manipulate the ranking results, promoting the adversarial candidate to the top. On the other hand, people notice information homogeneity phenomenon for recommendation systems in social media. It is because they generate information cocoons or filter bubbles, which provide biased information based on user preferences, thus narrowing people's perspective. Further, in scenario of searching for information on public topics, the issues arising from the reliability defect go beyond returning irrelevant results. Search results in public topics usually includes opinions with different stances. Manipulators can rank the items based on their stances rather than relevance, leading to unfair ranking. This is opinion manipulation, and it can make ranking top dominated by similar opinions, close to opinion homogenization caused by information cocoons. The cocoons. An example of information cocoons is that during the COVID-19 epidemic, most people only consume information in favor or against vaccines, not both, contributing to the vaccine avoidance in the society. Therefore, in the retrieval of public topics, we expect to fairly display opinions with different stances, helping people with critical thinking and fostering a more tolerant and inclusive society. However, the threat caused by opinion manipulation is greater than that of information cocoons. Information cocoon is originated from personalized needs and it mainly targets individuals, while opinion manipulation generally stems from ulterior motives and targets groups of people. Therefore, opinion manipulation damages the retrieval reliability and ranking fairness in a more profound way. Opinion manipulation can let manipulators guide people to think in a certain direction and hold certain opinion. Some research finds that manipulating search engines to produce biased results could alter voting outcomes. Moreover, opinion manipulation can influence public opinion on controversial subjects, even leading to cyberbullying and internet rumors. However, current research on manipulation to opinion stance mostly relies on video work, struggling to identify the reliability weakness of neural network models. Also, there is limited research on opinion manipulation in information retrieval, so we need to explore the visibility of automated opinion manipulation and its impact, assessing the retrieval reliability and ranking fairness of neural network models. So here we have the 3 research questions. To answer the first research question and to achieve automated opinion manipulation, we conduct ranking manipulation under a white box setting in which manipulators can access complete knowledge of the victim model. Starting from the simple white box setting can lay the foundation for future research. Also, for stance detection, we adopt machine learning methods due to its superior performance. Here are 4 typical methods for ranking manipulation in information retrieval, from rule-based to gradient-based. Gradient-based methods can be applied to automated manipulation in scale. Hot flip is just one of them. Other gradient-based methods like collisions and PAT, they add semantic constraints to the perturbation, improving the manipulation performance. Therefore, we conduct manipulation with collisions and PAT to assess the reliability and fairness of opinion retrieval. In addition, we adopt transfer learning by fine-tuning BERT to construct the stance detector, as BERT achieves the best detection performance for many datasets. In automated opinion manipulation, we initially fine-tune BERT to construct an opinion detector and rank articles from fake news challenge dataset by BERT model. Subsequently, the detector is employed to check
whether opinions exist in the articles and, if present, to identify the stance of these articles. We select low-ranking articles with a certain stance as the target. After that, collisions and PAT are adopted to generate perturbations for the target items. These perturbation triggers are inserted at the beginning of the target articles, and we re-rank these articles to evaluate the manipulation performance. As we can see in the diagram, the three types of perturbation can significantly achieve automated manipulation. And the example in the bottom right corner shows the case of using PAT for opinion manipulation in the retrieval for a certain public topic. Then, to explore the practical manipulation impact, we designed a simple user experiment. We gathered 10 subjects and divided them into group A and B. Separately, read the research results before and after manipulation. The perceived credibility rated by the groups is shown in the diagram, and there is a significant difference in the perceived credibility before and after manipulation. It demonstrates that automated manipulation of opinions ranking is effectively impacting users' perception. In conclusion, we successfully confirmed the feasibility of automated opinion manipulation and its impact. Reliability weaknesses and unfair ranking in opinion retrieval have potential risks. In the future, we would like to try some ways to deal with this problem, like ranking based on the combination of stance and relevance, using variable algorithms or visualization. And the final part, these are the research limitations we have summarized in this paper and potential improvements for the future. Thank you for listening, and I'm happy to answer any questions you may have.
Any questions? All right.
Any questions?
So we got one last in-person presentation. Let's start. Thank you.
GPTs by retrieval augmented generation poisoning. Since we are kind of running late, so I'll just quickly go through the background and go into the methodology. So for those people that are not really familiar with large language model jailbreak, so jailbreak is basically just the concept of prompting the large language models to generate some contents that violates the usage policies. One particular example is that you can actually ask the large language models to generate, for example, harmful information, which is not preferred in this case. It is worth noting that different large language model service providers will have different types of policies. So for example, OpenAI restrict their ChatGPT models to not generate any harmful information, private information, and also adult information. BARD will have different usage policies, but generally that's the concept behind. Another one is retrieval augmented generation, which has also been mentioned in the previous presentations. But the general idea here is that people can extract the data from external resources, such as local documents or online resources, and provide them into the large language models for the content generation. So RAGs are mainly used to generate more accurate information and avoid hallucination in large language model prompting process. A very concrete example of utilizing of RAG is the recent OpenAI GPTs. I believe many of you have used this before. GPTs are available to all the ChatGPT users, and it has an estimation of more than 180 million users. So the general concept of GPTs is that
user can actually provide an external document uploaded by the GPT creator, and this document will be embedded into the system and provided as a part of information to the large language model. So whenever the user is asking any questions as the prompt, this prompt together with the external resources will be provided together to the large language model for the prompting. So you can imagine that the ChatGPT will actually have the knowledge over the external documentation. Our main motivation and goal here is that we realize that these RAGs can actually be controlled by some malicious users. Because when someone tries to create an GPTs, for example, he could actually upload whatever documents or information available to the OpenAI and then ask the GPTs to use that document for the creation of this whole thing. And also, one more thing is that the created GPTs can be shared to anyone, and the other people can use these GPTs as if they're using a normal ChatGPT. So our goal here is to achieve effective jailbreak through the controlled RAGs, which means that we are trying to find out a way to jailbreak the ChatGPT models based on this RAG feature. So our strategy is a three-step procedure to construct the malicious GPTs. The first step is that we collect some malicious information from the online resources and also those unfiltered large language models, for example, Mistral, to create the malicious information over a particular topic, for example, harmful information. The second step is that we actually need to create the document from those malicious information. We are using several engineering tricks to bypass the filters applied by OpenAI. For example, they will filter out those documents that have a malicious file name. If you upload a file name that is, for example, how to make a homemade gun, this information will be identified by OpenAI and cannot be used by the GPTs. But if you just like name the file as usage documentation, then the API, the OpenAI API can actually retrieve the information from the file. And also, we are trying to use the PDF formats, which is because that we notice if the file is uploaded as PDF, then it will be vectorized by OpenAI API services. If you're using a text file, then it will be directly used as a prompt and will go through the content filtering mechanism. So the third part is that we will design a series of malicious content triggering strategies. In particular, we will prompt the user to use proper questions to trigger the jailbreak. In GPTs, there's a sample question feature to guide the users, and we will just like use this feature to guide the users to ask the correct questions. We find that the key here behind the RAG poisoning is that although there are some implemented defense mechanisms by OpenAI and also other large language model providers, the key here is to deceive the large language model to consider that they're actually rephrasing the malicious contents from the external resources, the RAG files, instead of creating the malicious contents on their own. So a working example of the prompt here is that your GPTs help with answering users' requests by retrieving the knowledge from the knowledge files and extending them to formulate the final answers. In this way, we noticed that we can actually bypass all the security mechanisms implemented by OpenAI and actually achieve jailbreak with some very simple strategies. On the right side, there's a link to our sample GPTs, but I will also do the live demonstration now. So the idea here is that if you ask ChatGPT, GPT-4 directly how to build a homemade gun, the answer is quite simple. I cannot assist with that. But once we create this very specific GPT's example, I think I need to refresh this a little bit. Once we have created GPTs with particular uploaded documentation, you can see that the GPTs will actually first try to retrieve all the malicious information from the external documents, and then try to revise the information to see how to answer this particular question of build a homemade gun. So in this way, we can actually achieve the jailbreak. This is only an example on this particular information. We also have another example for the money laundering through GPTs. But actually, people can create arbitrary information and provide them in the document to achieve the jailbreak. And lastly, you can see, oh, sorry, there's a network error here. Our attack strategy achieved a very high success rate on both GPT 3.5 and GPT 4. In particular, if you ask those kind of malicious questions over 4 different types of malicious topics, adult information, harmful information, privacy, personal privacy information, and illegal contents, the direct answer rate is very low, but if you're using this GPT strategy, we can achieve a quite high effective jailbreak rate. As an ongoing work, we are also trying to reveal some further mechanisms behind this RG poisoning strategy on jailbreak. So what we're trying to do is to firstly automate this whole pipeline and also try to improve the efficiency and try to explore more complex and varied scenarios in RG poisoning. Also, we try to enhance the RG poisoning interpretability by and revealing the mechanisms behind. So that's all of the presentation. Thank you.
All right, thank you. Thank you. I really appreciate everyone. This time we really hit a serious technical issue, and I'm really glad everyone still stick with us. And all right, that's all for the first time, the AISCC workshop. And yeah, hope everyone have a great conference experience in the rest of the days. Thank you. Thank you.